Oh, good. My screen was covering up half the drawing, so I was, now I see what's going on. So we'll give it another couple of minutes for stragglers and for all these wonderful drawings. I love the drawings. So we've got some low solar corona. Mark and I stole the easy ones. Looks like we've got a little reconnection going on, some flares and reconnection. Like radiation belts, sunspots, something something about ionization, photoionization that I can't quite figure out. Let's see. So,
was just thinking of a cartoon having the two dinosaurs sitting on Earth looking at space and saying, is that another asteroid coming? And it's actually a CME. How about that? Because whenever I think of
see
cartoons,
you draw that, Mark.
Oh, I see. I think somebody's drawing the entire Sun-Earth connection.
there's the dinosaurs. Awesome.
Well done, Brandon.
Okay, people should put the finishing touches on their masterpieces. You don't have to erase it. It doesn't have to be perfect. Okay. So I grabbed a screenshot of that. I'll give you one more instruction and we'll get started. Put a heart by whichever one. So you should have on your annotate, right? You should have a stamp function. Put a heart by whichever one you like. You is your favorite, right? I only see about less than a dozen hearts. So it should be 35. All right, last chance to upvote your favorite. All right, going once, going twice. We'll get rid of George Winston. And let's get started. Good morning. Feel free to turn on your cameras if you can, if you're in a position to do so. It's always great to see everybody's faces. Maggie, do we want to start off with a group photo?
Yeah, that's great.
Okay. Usually, I mean, we've taken a little bit of time to get to know each other. Usually, we do this somewhere in the middle, but I think there's a reason to get it early, and then we'll start some introductions and tell you what the plan is for today. So if you can turn on your camera, that's great.
Okay, I'm gonna do this in 2 rounds since there's so many of us. I have a couple pages, so if everyone can smile really quick. 1, 2, 3. Great, and then the last one. 1, 2, 3. Perfect. Thanks, everyone.
Okay, great. All right. Welcome everybody to our first full session of the Heliophysics Summer School 2022 edition. So we've been at this. We realized that this is our 16th summer school running since the the mid 2000s, and so we've been at this for a while now with a variety of different deans and variety of different speakers, and of course each year a new set of students. And so welcome everybody to that. My name is Nick Gross. We've already interacted several times. So I'm at Boston University, and I primarily work on education projects and professional development for graduate students and early career scientists. And this is part of what that work is not only having you develop your content knowledge in the field, but also having you develop some networking and some community. And that's a big thing, because you will find that the people that you're going to interact with at this school, even if we're interacting in this virtual environment, you're going to start to see throughout your career. You're going to revisit them, show up at conferences together, start seeing their papers, start seeing other work that they're doing. So it's important then that we start to build a community that you can take forward and build your network of people that you're working with. So also the other person you've been engaging with is Maggie Costley, who is going to be supporting us for the entire school, and has been very valuable to keeping things going forward and making sure that we're organized. If you saw the room I'm in right now, you'd know that organization was not my strong suit. So, and so Maggie, can you say hello? And is there anything that we need to know that I've missed?
I don't think so. Hi, everyone. It's great to see all of you guys. Thanks so much for responding to all of my emails when I send you something and request something in return. But yes, we are recording these sessions. So just in case you weren't comfortable being filmed and didn't want to fill out the consent form, then yeah, make sure that your camera is off. But I don't think there is anything else for
great.
logistics wise for this first session. So yeah.
Great. All right. Thank you, Maggie. There's 3 other people I wanted to have spend a little bit of time well, I won't introduce them, they'll introduce themselves and talk about what their sort of hopes for and dreams and aspirations for the summer school are. And so I'll start with Mark Mulwin, one of the deans of the summer school.
Good morning or evening, where everybody are. I guess that's one advantage of a virtual, is that you get to greet everybody in their local time zone, though it'd be better if we're all local time zones. I guess it would be kind of wild if we all only went by UT time. But I'm a professor of climate and space sciences at the University of Michigan, and my education is in space physics, and I've been getting into, over the last 20 years or so, more space engineering. One of the things that I do is build magnetometers, and we've been developing a new type of magnetometer called magneto-inductive magnetometers that I hope to revolutionize the way magnetometry is done in space. I've been very interested and involved in teaching and in higher education, workforce and development issues. I've co-chaired the last decadal surveys working group on education and workforce that really got me into some of the education and education research community. I was the inaugural president for American Geophysical Union's education section. So if you're planning on attending AGU, you should check out all of the education sessions, not the least as Upgoer 5, to see if you can communicate in the 100 most common words in the English language. But the HSS, the Heliophysics Summer School, is sort of the old person of summer schools. If you've noticed, there's dozens of summer schools given internationally each year. And the NASA LWS Heliophysics Summer School has been running, I think Nick said 16 years now.
Yeah.
And I was fortunate to be invited to guest lecture in the first one. So this is fun coming back as the dean. And I hope we have a chance to get to know each other, even though everyone looks really little in your Zoom room. And please do introduce yourself if we haven't met and run into each other at AGU or some other professional meeting. It would be great to meet you in person.
Great.
Should I ping pong it over to someone, or do you want to?
That would be great. Well, why don't we go with Christina, and then Hannah.
Hi, everyone. I'm Christina Cohen. I am at Caltech, which is in Pasadena, California in the US. And it's quite sunny here. It'll probably be very warm soon. I study solar energetic particles. At our group, we build instrumentation that we put on various spacecraft, and hopefully they launch without a hitch and then go up, and we download the data, look at the data. It tells us, generally we send them outside the Earth's magnetosphere. We're studying material that's coming from the sun in terms of energetic particles that tells us various things about the composition of the sun, as well as acceleration mechanisms, and of course taps into space weather and all that exciting stuff. I've been doing that for longer than I would like to admit, including also in Pasadena, longer than I'd like to admit. While I've participated in various different summer schools in the past, this is my first time with this one. My first time as dean, so I'm pretty excited about that. I do wish we could all be together, but it is kind of fun seeing everybody from all over the world in their different, I guess mostly in their different rooms, but I also enjoy looking at the different still photographs you guys have. That's kind of neat, trying to guess where everybody is. Hopes, aspirations, and dreams, well, that's a pretty tall order, but mostly I just hope we have a chance to get to know each other. I hope some point I will meet you guys in person, maybe at a meeting or such. Definitely, if you see me wandering the halls anywhere at any meeting, come up and say hi. I'd love to see you all in person. And I hope that we all learn a lot this week and have a lot of fun doing it.
Okay, great. Thanks, Christina.
Sure.
Christina and Mark, as I said, were our deans. They have been instrumental in organizing the program and deciding, inviting lecturers and picking some of the leading voices in the field in terms of space physics. And so we'll hear from a wide, also a diverse set of voices in the field, I should say. And so we'll hear from a wide range of people. The person who's been leading this effort, in particular, on organizing and also funding, is our director of the UCAR.CPAESS program, is Hannah Morello. And so I think she'd like to say a few words.
Thank you very much, Nick, and hello, everyone. My name is Hannah Morello, and I'm the director of the SPS-CPAESS Center here at UCAR. I'm delighted to welcome you all to this year's Heliophysics Summer School. The Summer School is a NASA-funded event that has been held since 2007, and we are very grateful to NASA and Lika Gutha-Hakota for their strong support. As you know, the summer school focuses on the physics of space weather events that start at the sun and influence atmospheres, ionospheres, and magnetospheres throughout the solar system. This year's theme is connecting the heliosphere, using global models to connect in situ and remote sensing data throughout the heliosphere. I know you have an exciting summer school ahead of you, and I would like to sincerely thank Dr. Nick Rose, Boston University, Dr. Mark Moldwin, University of Michigan, and Dr. Christina Cohen, Caltech, for their planning and support. I also want to take this opportunity to thank Maggie Cosley from our own CPAESS program for her event management support of the summer school, as well as Katie Lackey for her help with all the summer school applications. So once again, welcome to this year's Heliophysics Summer School. Thank you.
Okay, great. Thank you, Hannah. Thank you so much. So our plan for today, in the first session, we're doing some introduction, and that will run us up till about 9:30 or so. I'm doing the conversion in my head because I'm on the East Coast, yeah, that'll run us up to 9:30 or so Mountain Time, and at which point in time, around 10 o'clock, Karel Schijver, the editor, the author and editor of the text that you've been working on, and also the creator of the activities that you all have been working on in your time zone groups, will join us to run through a series of a discussion of those activities, and using your input as guidance, and also some of your discussion that he'll prompt. So I certainly want to prompt you to speak up with Karel. He will invite you to talk about things. So, and the trick is to not be shy. So we'll see if we can prompt that. Before I want to do two other things. And then I'm going to send you into your breakout rooms, into a set of breakout rooms, and we'll give you some instruction as to which breakout rooms to go into, to give your elevator speeches to each other. So as I said, the goal is to make sure you're introduced to each other and you're working with each other. We're going to have a wide variety of opportunities to mix you up, both in your time zone groups, but especially in these synchronous groups that we're doing. So let's figure out, let's do in two ways. We're going to figure out where everybody is. So if you go to the three dots in the upper right hand corner, you should be able to hit rename, and you can put in the name you like to be called, your pronoun. If you want, you can put in your pronouns and your location. So here is my example. So I like to be called Nick. My pronouns are he, him, and I'm in Boston in the USA. Okay, and some of you are masters of this already, so you've all got that. Everybody find the way to rename yourself. Anybody not find the way to rename yourself? Just you can go to the bottom right and either raise your hands or put in the open mouth surprise face or something, and we can help you out. All right, looks like most people have figured this out. Great. Okay. The other way we can tag ourselves and figure out where we are, just to see the sort of problem that we're managing here, is I'm going to share a world map. And on that, you should be able to annotate it with a star. Put a heart where you were born, and a star where you currently are. heart where you were born or grew up, wherever, whatever you want to identify that as. Oh shoot, I think I messed up. Okay, no, you don't get to take remote control of my screen. It should be just annotate.
We have several people born on the ISS, or
Yes, I'm not quite sure what. I think I lost control of my screen
okay.
for a minute because I was all right. Oh, the map I chose was bad because the star kind of fades into some of the colors on the map. Okay, lots of people studying the US, people in India.
I was born probably 25 miles away from where I live. I feel like
Oh,
I'm in the Middle Ages, so I've left and came back.
Yeah. Excellent. All right. Okay, still some action going on. People trying to figure out where they were born on the map. All right, so you can certainly see the challenge that we have in terms of spread of time zones. We've got people studying in India and China, as well as people studying on the west coast of the U.S. It was not quite as challenging as last year. Last year we had 3 people who were in Hawaii, and so they were, to balance that, they were getting up at pretty early in the morning, 4 o'clock in the morning, to participate, while some people in India were going to bed well after midnight. By the time it was all done, this is still an interesting challenge, and want you to appreciate that some of the people you may be talking with are in different time zones. As you interact with everybody, I believe that Maggie asked you to fill out a code of conduct, or acknowledge a code of conduct that that UPass and CPAESS and UCAR take advantage of, and the code of conduct more or less tells you what not to do, right? And so what I want to tell you is what to do, and what to do is, as we're interacting with everybody, as we're engaging in discussions, as we're challenged by the physics that you're engaging with, I request that you spend time being kind to each other, right? And taking responsibility not only for your own learning and your own development, but also the development of all the people you're working with. And so it's not just about what you do as an individual, but also about what the group does. You will find that as you go forward in your career, we very, very rarely in science, even when we tell the myth stories about Newton and Maxwell and Faraday and all of these and Einstein, we tell these tall pole stories. They didn't work in a vacuum. They didn't work on their own. All right. Even in the day of Newton, he's exchanging letters with people, even if they're kind of like real polemics against who's I'm looking for the guy who invented the derivative symbols. Leibniz.
Leibniz, yeah.
Leibniz, yes. you know, they're communicating with each other. And you know, Einstein isn't working. Einstein's part of a community, right? He's not working on his own, in spite of all of the myth that blows up around this. And that today is even more important than anywhere else. You're part of a community. You're working as part of a team. You're collaborating with people. None of these things happen. We don't launch rockets. Space missions don't happen by one person, you know, putting the rocket together. It's a collaboration. It's a cooperation, and the more you can collaborate positively with somebody, and work with them to bring forward all of the ideas, the better you are, right? So as you're talking to people, I encourage you to invite everyone to the table, as it were, everyone to participate in the discussion, make sure that everybody's following along, that you're not leaving anybody behind in the discussion. And that's going to be true in the next couple of days in particular, because we're going to throw you in. I'll explain a little bit more later, but we're going to throw you into the deep end and on something and say what and have you work on some things, and I'll explain a little bit more about that later. All right, great. All right. Yep. Mark and Christina, you have anything to add on that?
The only thing to add is to remember that you're probably going to be an expert on a topic within your room, so feel free to play that role. And if you're not contributing to discussion, think about why, if you can reflect on that, because we're going to be missing your expertise and insights and perspectives. And this cohort of students were selected as we look through to try to have good balance between disciplines and postdocs and senior grad students from different experiences. So I encourage everyone, if you are not an extrovert, to practice to be one. And if you are an extrovert, be conscious if you find yourself dominating, to let others participate as well.
Yeah, I would say it's also nice at various times to take a pause and just sort of go quickly around the room and make sure that everybody's said something, because sometimes if you're not an extrovert or you don't talk fast, sometimes it's hard to get a word in edgewise, even though you have something to say, and then you feel like, well, the moment's passed. But it's always nice to kind of take a second and make sure everybody's had a chance to say something. I will also say that during the times when we're in bigger groups, if you're uncomfortable just butting in, definitely use the chat. You know, throw your ideas in the chat. There will always be one of us that is sort of monitoring what's going on in the chat. And if the speaker or somebody needs to be interrupted, we'll help do that. And we can also answer questions, and other people can answer questions in there as well. So feel free to use all the tools at our disposal here to have meaningful conversations.
Great. Okay, great. Thank you, Mark. I'm just trying to understand your chat message.
We're talking about Einstein and such, so we had a group photo, and so one of the famous group photos is the Solvay conference that has a whole bunch of Nobel laureates. And Christina, not only was it in black and white, but there were only white dudes except for Madame Curie. But it was geographically diverse. I think there were people from Poland and the UK and everywhere in between.
Right. So hopefully we've certainly built the broadening of geographic diversity and inclusion here. All right, great. Okay, I am going to I think what I'd like to do now is I want to send you back into your breakout rooms. Christina, could you put up? Sorry, Maggie, could you put up the list, the synchronous group list? Is that can you drop
Yes,
that into chat so people
absolutely. Yep.
can? So this is just a reminder of your synchronous groups. The synchronous groups, you're going to work in those for today and tomorrow. By Friday, I'm going to swap those up so that you get to work with different people. And then we'll at least swap those up at least once more before the end of the summer school, so that you'll have several different groups to work with. There's what I'd like you to do now is if you should be able to download that or open it up. And I want you to go into your the breakout rooms, and I'll give you some instructions about doing that. And give your elevator speech to the synchronous group, which you've done before, but I'm going to double up. We're going to combine synchronous groups, so you'll have some new people to introduce yourselves. And also add to that a fun fact about yourself after you're done with your prepared elevator speech. Think of just one thing that's that you want to share with people that's a little unusual and outside of what your elevator speech is about. Okay. The way I want to do this is we're going to use 4 breakout rooms. One of them is going to be a little crowded, so we're going to have to make sure that we sort that out. And so in the first breakout room, we'll take groups 1 and 2 from the synchronous groups. The second one will take 3 and 4. The third one, 5 and 6. And then the fourth one, 7, 8, and 9. And that's the crowded one. So that's the one where we've got to make sure that we're moving along. All right. So questions on what we're doing before Maggie opens the breakout rooms? Everybody know which breakout room they're going to? Anybody not? Put your hand up if you don't know which breakout room you're going to. That is, and when I say put your hand up, there's a reaction button down the bottom that allows me to put a physical hand. Okay. So Yakub, you're in synchronous group 1, so you're going to be in breakout room number 1 with groups 1 and 2. All right, great. Everybody else indicates that they know what they're doing. So I'll ask Maggie to open up the breakout rooms. You go in there and share your elevator pitch and one fun fact about yourself. So, and you should be able to move yourself into the breakout rooms. So Christina and Mark, feel free to join. Okay, so we've already got people who couldn't figure this out. All right.
Nick, do you want to jump in breakout group 7?
Yeah, I'm gonna. Yeah, 7 and 8. So I'm gonna do that.
Okay.
Maggie, do we know who's in breakout room 5 by themselves?
I do not know. Do you want to jump in there or do you want me to?
I can go in there real quick.
Okay, I'm trying to see what group he belongs in.
Oh, they just left.
Okay.
So looks like I bet everybody got a little confused because we have 8 synchronous groups, and we only talked about 4 breakout rooms, and then everybody went, wait.
Yeah, yes.
Hi, I am trust that I supposed to be in group 4 or in group 2.
Yes, check.
What should I meet in 2 or in chapter 4?
Hold on just 1 second. I'm gonna look and see where you're in.
I'm in group 4 of synchronous, but I should enter in 2.
Then you should be in
You should, yeah, join
breakout
group
group 2.
Great, sorry.
Yeah, no, you're good.
Hi, Maggie.
Yes, hi. Okay, so you're in,
Mine is in the group 8, but there is no
yes.
people there.
So you're in group 9, I believe.
Oh,
Yeah, but
or 8.
so you'll be in breakout group 4.
4. Okay.
Yes.
Thank you.
Yeah, of course.
Hello, Maggie. Can you help me with the breakout group?
Yes, absolutely. Let's see which one you're in.
Looks like 5.
I joined. There was no. Maybe I will try
Not
again.
5.
So we're combining the. Mhm.
Go ahead,
Now
Nick.
We've been combining rooms, so group 4 and 5 are in breakout room 3.
All right. Okay. Thank you.
So Nick, did you get everybody that's in groups in breakout room 7 to switch over to wherever they're supposed to go?
I'm leaving 7 where it is because that's got the new person in it, and I'm having them. I've asked the 2 of them to catch her up as to what we've been doing.
Okay.
So that was the spontaneous sort of like, oh, this is a happy accident. We'll fix that. Okay. So
Right.
and feel free. So let's see, how are we doing? Where are we at? So
there's still one person in 5. I just went in there and there was nobody else there. So I don't know if somebody's bounced back or something. I don't know what's going on.
I think that's you.
It shouldn't be me anymore. I left the room.
Okay.
But
I don't see the one person. I don't see other than your sign there, but
yeah, that's weird. Okay.
Okay. Well, if you're assigned there, that was the last room you were in.
I see.
It just grays you out. So.
Right, but it didn't update the number or something, which is kind of weird. Okay. I just realized I can drop down these menus and see who's in which group. That's kind of fun. Okay. These are all the Zoom skills I should have figured out a while ago, I guess.
All right. I'm going to go into breakout room 4 and make sure that they're moving along. I'm assuming
Okay.
Mark dropped into a room.
Mark's in 1. I'll go in 3 is pretty big.
Yeah, 3 is pretty big. Just make sure they're moving along.
Okay. At what time are
And-
they supposed to come out of this?
Yes.
That was a time?
Where are we? So, Maggie, can you tell me where we're at in time?
Like what time is it, or
Yeah.
sorry?
What time? Where are we? So, Mark.
It's
Karel is
8:46
joining us at 10.
Carl's joining us at 10 Mountain Time. It's
Right.
8:46 right now.
Okay.
So yeah, an hour and 15 minutes until he's on.
Okay. So we have like a ton of time to kill. So certainly we'll let them go until the top of the hour. And we'll see how things are at that point. And then we'll we'll figure something out from there.
Great. I'm gonna pause the recording in the meantime.
That's good. Okay. All right.
Mhm.
Christina, you're going to 3, and then I'm going to 4.
Yep. All right. See you in a bit.
All right. Breakout room 1. Did we interrupt anybody?
I was giving a lecture on magnetoinductive sensors.
Oh, I see. Okay.
They asked a question about my elevator pitch.
I was going to say they asked a question about something completely unrelated to magnetoinduction.
yeah,
Then you just went there, right?
Let me tell you about this really cool thing.
Right.
I reject your question and replace it with one I can answer.
I'm having a hard time hearing. This is what I think you asked.
That's the art of being a professor, right? All right, great. Thank you all for doing that. So room 1. What's somebody from room 1? I don't care who. Tell me one fun fact you heard about somebody else in your room.
Everybody loves Manchester United.
Okay. Somebody who isn't a dean in the summer school. Okay. Tell me one fun fact you heard about somebody else in your room.
Extra points if it involves magnetoinductance.
Right.
I learned that somebody grew up in Alaska and got to play with huskies as their job growing up.
Excellent. Okay, great. Thank you, Brandon. Somebody from room 2. I guess you were in room 2.
Yeah, I went in room 2. Sorry. I
Okay,
jumped
no
ahead.
problem. All right. Nobody else from room 1?
Yeah.
Miriam?
Hi, Nick.
Go.
This is Shorik. So the fun fact that me and Mark both share is we both are foodie and we both love to travel. Although I don't mention that I love to travel and eat food from wherever I go, but Mark did mention that. So yeah, that's a fun fact from us.
So what's the most unusual thing that you have eaten?
Okay, so I am a meat eater. So it was a full front-sized leg of a goat, and it took me around 2 hours to complete. So yeah.
Okay, well that's impressive. Okay. All right, great. Somebody from room 3, which should have been groups 5 and 6. Andrea, Ashtush, Partek, Miguel.
Well, we had a couple people in our group who talked about their different backgrounds that were not necessarily what we'd expect, like a straight line. Miguel talked about going into oceanography and radio astronomy and all these things, and Astos talks about how he had they study condensed matter physics as well. So there's definitely a diverse set of backgrounds in our room.
Okay, and somebody from room 4.
We learned that Florian is a 49ers fan.
Excellent. Okay, I was wondering. Yeah, I heard him say he was a fan of American football, but I didn't get a chance to find out which team. What? Not a Boston Patriots fan?
No, that would be too boring.
New
Everyone in
England
Germany is
Patriots.
either Patriots or Seahawks somehow. Everyone in
I
Germany.
see, okay. All right, good. Thank you for sharing that. And so, feel free to have those kind of discussions and share with each other. I find that helps grease the wheels a little bit, and the social wheels, and as you find out more about something, you're less likely to tell them that their ideas are stupid if you know that they like to play with huskies. So, great. I think we're going to take a break for a little while, but before we do that, Maggie, so on this sorry, I started 2 thoughts at the same time, and it doesn't work. This coming Saturday, so a week, at the end of the week, the session we have scheduled is for you all to give a short presentation about your the work that you're doing. And that's going to involve both a quick elevator speech type advertisement for the particular work, and then what we're probably going to do is send you in 2 or 3 at a time into different breakout rooms, and have you present in a short presentation, and then take questions and discuss with your colleagues about what you're doing. The idea is that, as Mark already said, you are in terms of the work that you're doing. Many of you, almost all of you, have started some kind of research already. In terms of the work that you're doing, you are the experts in this room on that work, right? Even with the experienced scientists that we're bringing in to lecture to you, they don't know what you've been doing because you're doing it, right? And so you have an opportunity then to share that work and be that expert in on this Saturday. Maggie, do you know how many people have asked, have given you a title or said that they were willing to present?
Yeah, we have about 7 or 8. But Nick, I have received a couple questions regarding how long the presentations should be. So maybe that would be a good time to talk about this now.
Sure. I think the presentations are intended to be short. In the past, what we've done is, when we were in person, what we've done is we've done short, like 1 slide, 5 minutes, or maybe 2 slides in 5 minutes, and or posters. We've got a little more flexibility in here because of because we can use the breakout rooms and people can go around. So I think of it as much of a poster session as anything else. And so you can either present one big slide that's a poster, or you can have a few little slides but not spend too much time on it. The idea is to get you talking with each other rather than doing an AGU style 10-minute. So more like lightning talk formats, and so that to prompt people to talk to you about what you're doing rather than give a 10-minute presentation. Right? The 10-minute presentations, it would take us too long. I'm a little surprised that we have that few people taking it. If you put a heart, either a heart or a thumbs up reaction. So down at the bottom, you should have a reaction button. Put either a thumbs up or a heart reaction. If you intended to send Maggie a title and haven't done it yet. Okay, there's one. And Mark is encouraging, there's a couple, okay. So we've got, so we've got like at least 4 that I'm counting on now. So so send Maggie a title. It does, and this doesn't have to be, this can be something that you've put together quickly. It doesn't have to be a polished thing. This is just happening internally. We're not going to have we won't have the head in NASA here to scrutinize your work or anything like that. It's more or less just to share what you're doing, give a little advertisement for what kind of work you're doing, even if you don't think it's ready to share in prime time. You can at least talk a little bit about what you're doing. So so in the next day or so, just so we can make sure that we're organizing this properly, send Maggie a title. Then what are we asking for, Maggie? Just a title?
Yeah, that you're interested in a title.
Great. And and we'll get that organized. I just want to make sure that I know what I'm going into, like Saturday morning. I know what we're doing and how many breakout rooms we need and all that sort of thing. Right? Great. Any other questions on that or anything I didn't make clear about that? Going once, going twice. All right. And bunch of things in chat that I missed. Anything? So lightning talk format. Okay, Mark. Mark, you want to say about something about taking that opportunity?
Yeah, you probably realize it by now, but you're going to become a professional writer and speaker. That's what scientists and engineers do, is that if you do research and you don't communicate it, you didn't do it. And so practice is always good. And since this is such a short, 2 to 5 minute, 1 to 2 slide, if you have any ideas, but it also allows everyone to get to know you a little bit better and the type of work you're doing.
Great. Okay. I think at this point, we will take an extended break until Cal Schijver joins us. So you're welcome to leave to stay
Karel's
connected.
here.
Well, I'm sorry?
Karel's here.
Karel is here, but you tell me when you want me to start, anytime.
Well, okay. When were you thinking we would start?
You told me to start at 9 my time, 10 your time.
Oh boy.
But I've got it already, so whenever you want to start.
Does anybody need, so let me ask you this. Does anybody need, we're all in different time zones, so there's different needs. Does anybody need more than a 15-minute break from this? So somebody put your hand up if you need more than a 15-minute break. Okay. Okay, so we've got a couple of hands for a longer break. Can we take a 20-minute break? Will that work? Okay, I'm going to go with a 20-minute break, and then we'll start with Karel's session. Karel, does that work?
Works fine.
Great.
So 35 minutes past the hour?
Yes.
All right, I'll be here.
Okay, great. You're welcome to stay on and or and just mute your mic and turn off your camera, or you can log off and log back on as you see fit. And we'll see you at 35 minutes past the hour. See that you're here. Okay, so we've got looks like we've got a lot of people here. So we're going to get started. For this session, I'm going to turn it over to Karel Schijver. Karel, along with a extensive career, providing us, the entire community, with gorgeous pictures of the sun in all wavelengths, and allowing us to view the sun in different light, which is a lab there. What do I say? Oh yeah, it's viewing the sun with different eyes. That's one of the labs that I have put together for other summer schools. You looking at various at SOHO and SDO imagery, and Karel has also been the dean of this summer school on two different rounds, and has influenced its progress and its direction significantly, including the inaugural dean along with George Sisko. And we've invited him not only to give his take on that, but also take us on a little bit of a journey through some of the activities that he has in the volume that he's collected from the chapters that were written by various lecturers in the summer school. And Karel's collected those into a volume and that he's edited and added over something like, it's about 200 activities. Is that right, Karel?
It's a little over 100, but maybe there will be 200 at the end of this school.
Okay.
Who knows?
Okay. Certainly a large number of activities, many of which I had the pleasure of reviewing and seeing if I could do them, and getting a lot of insight from that. So I thought it was a valuable place, and we will have an opportunity to review some others throughout the summer school. But you all spent some time reviewing hopefully all of the activities, but certainly as in your time zone groups, reviewing the ones that were assigned, and we got some valuable feedback and some interesting comments on the Slack channel. And so I'm going to turn it over to Karel, and he's going to take you on a journey through that, and hopefully prompt some discussion.
All right. Well, hello, everyone. Good morning, good afternoon, good evening, wherever you may be. Maybe some good night. It's 200, more than 200 activities. You're right, Nick. I should read my own book occasionally. Yeah. So I'm Karel Schijver. I prefer Karel, although yes, it's spelled as if it were Carol, but I'll go with Karel. And I started a long time ago as a stellar astrophysicist, interested in stars like the sun, interested in their coronal activity predominantly. So one of my first activities was working on the newest X-ray spectroscopy taken at the time of stars. And I was very rapidly very frustrated with the fact that you couldn't see what was going on stars. So I turned my eyes to the sun pretty early on, already in my thesis work, working on old Skylab data, for which I had to dig up 5-track tape readers. Now, most of you don't know what tape readers are. 7-track tape readers were really curious things at the time. It was very hard to come by. Anyway, from there, I migrated into solar activity proper, then the heliosphere, then space weather, Right now I'm drifting back to the stars, to exoplanets. So I'm basically probing everything that is the field of essentially heliophysics. And I'm glad I did. When I came to this country a while ago, I've been here half my life, so almost 30, more than 30 years now. I found myself on occasion reviewing proposals on topics that I knew very little about. I found myself in advisory committees, eventually at NASA headquarters or at the National Science Foundation, listening to people working in the other disciplines of heliophysics, having a hard time appreciating why they thought certain things were important or difficult, worthy of investments in terms of research, in terms of instrumentation. So when and that means that I had to learn heliophysics the hard way. So I envy all of you. Not that heliophysics has gotten any easier, but heliophysics has become accessible because there are now teaching materials and such available. And I was fortunate when Lika Guhatakurta from NASA headquarters put me together with George Sisko, who unfortunately died earlier this year, to start the Heliophysics Summer School a long time ago. And we started with books because there wasn't anything else. Nick stepped in at some point to help us with all the activities, many of which you are going to be doing. And we went through, I had the luxury of being able to invite people from all these different disciplines and tell us, teach me, teach everybody in the school, and hopefully with the books, teach you all also about heliophysics. Now, this book has been a work in progress. The series of books have been condensed into the book that you're working from. I hope you will take the opportunity to tell me where I went wrong. Just tell me where the typos are, but also where the thought errors are, or where I make leaps that you don't understand, because it's an electronic book. It can be updated anytime. So you can contribute to making it more intelligible. Now, what I'll try to do here in this, I don't want to call it a lecture, although I'll be talking a lot, obviously, but also looking at your activities and what came back from your activities, is give you a feel for scales and processes in the sun, the heliosphere, the Earth, and the other planets, because I happen to think that intuition is a really important thing in your science. If you want to make a breakthrough, if you want to discover something, it often happens because you have this feeling that there's something new there that you can actually understand, something new that you can discover. But in order to be able to know that it's new, you have to know what's already known. And in order to be able to connect the dots and make that discovery presentable to the community, you need to know what's going on in other fields around you. And also, I think, because I've learned, and I think many of your colleagues that have been in the field for a long time have appreciated that many discoveries are made at the interfaces of disciplines. So knowing what happens next to you is generally a good thing. I would like to encourage you now and throughout the school to ask questions, because I think it's already been said in the introductions earlier today, most of you are out of your depth in most of what's going to be said. I'm out of my depth in many of the things that happen in heliophysics. There's no dumb questions, if you want to put it that way. They're questions that basically reflect that you haven't worked on something. Your expertise is somewhere else. So speak up. It'll be hard to do in this Zoom session, but chat your questions. I think Nick is keeping an eye on the chat window that I'll keep an eye on, but I can't look everywhere at the same time. If I say something that you think is wrong, I'd like you to just speak up, because if I go wrong, there are 37, well, you know better though, so 36 other people on this Zoom call that will hear something that then isn't right. So please do correct me when I go absolutely wrong. My plan is to go through your responses to the activities, not all of them. What I did was basically look at Nick's list. And before I saw your answers, I picked one of these activities that will go first, and then second and third, and however many there were on the list. So I'm going to just do random selection in a way of your responses and talk through them a little bit. Ask questions if it isn't clear. Again, type in your ask questions. And I've made a file that I'm going to share shortly on the screen with you of the answers that I had and or some collections of answers that you gave. I will share that file later today as soon as we're done looking at it, and I may have to correct it here and there. So I'm going to start. I'll go try and share my screen and see if that works. Can I do that? Let's see, what do I want to share? This window, a portion of my screen. Are you seeing that screen?
Yes.
Yes, all right. So I'm going to start with the questions that I sent around, that Nick sent around, that I put together for him. And the first one had to do with essentially what powers the solar wind. Sorry if I'm looking over your head, my second screen happens to float above here, so I'll be looking off screen. Essentially, the question was what powers the solar wind? And I asked groups 5 and 7 to look into that. So I'm going to go for group 5. I'm going to have to move this screen a little bit because I can't see where group 5 went. Interestingly, both of the groups did much the same thing. You said, I can start with this equation, or group 7 actually started an equation even earlier, regrouped the terms and did pretty much what I thought would be the answer, except that you both chose to go for an integral form of it, which of course is an elegant way of doing it. And then they say, well, here, you can recognize the terms. Here's multiply everything with a density. Here's a kinetic energy term. Here would be a potential energy term. And the thing in the middle, well, the thing in the middle is reflective of the fact that one way of changing a volume is by stretching the volume, and that comes out of the gradient of the velocity. This term here, I guess, oh, I should be able to highlight this. That might make it easier. This term here, the gradient in the velocity. And the second way by which you can expand is sideways, which essentially is the geometry of the system, that term, because you're in a 1/r, sort of the cross-section of the spheres increase as r squared. So you get something that is proportional to a 2r in there. Group 7, I think, did much the same, wrote it down slightly differently, started from the equations a little earlier, but eventually came up with the same thing. Yes, these two terms, they said, these two terms reflect the fact that there's work being done by the acceleration, the stretching of the volume elements by the gradient in the velocity, and the geometrical configuration, the r square of the geometry. Yes, that is in fact what I did too, except I wrote it down slightly differently. I said, well, I stayed with the differential form, regrouped the terms a little bit, and then said, well, I can write this as a change in kinetic and gravitational energy, and that equals a work term. This is the geometric term. This is the stretching term. And with the continuity equation, I can rewrite that into saying, this should look like work being done by an isothermal gas expanding. So we came up with the same answer there, which is good. It is indeed the work done by the expansion of the gas that pushes the Parker solar wind out. That isn't quite the answer though. What powers the solar wind? Well, what powers the solar wind is the temperature of the gas that allows it to expand. But if it expanded freely, the temperature should drop because you've taken energy out of that parcel. Now, Parker said, I'm going to assume that the temperature is the same. By doing that, what he essentially said is that we have an infinite conductivity of thermal energy from the corona, mainly by electrons flying at high speed along the magnetic field out. And so the real answer to this question is what powers the solar wind? It's coronal heating. Parker assumed that he could describe the solar wind by things called pressure and temperature. And I'm going to come back to that issue in just a moment. He also assumed that the coronal temperature was constant. Well, it isn't, because at the corona, we're talking about somewhere between 1 and 3 million Kelvin. By the time you get to Earth, something interesting happens. Not only has the temperature dropped, but you also see a difference between the electron and the proton temperatures. And that essentially means that, no, you're not having an infinite conductivity, which is really a good thing. I'll come back to that in just a second. But also that the electron and proton populations aren't coupled the way that he had imagined it in a real hydrodynamic model of the solar wind. And why that is, we'll come to, I think, 2 questions from here. Now, this constant temperature thing is a headache. And I wrote down words here. I'll give you the gist of that. I'll share that file, as I said, because this particular Parker wind model does not stop accelerating. It basically goes to a speed of infinity, or, well, somewhere the light speed. And that means it requires infinite energy. And you can have infinite energy because it has a 0 temperature gradient and the temperature is everywhere kept the same. That's not realistic. So in a better approximation, you basically say, I'm going to include a third equation, not just continuity and momentum, but I will actually have conductivity so that there is an actual temperature gradient with a thermal conduction coefficient here, which immediately sets the total amount of energy available. You can work through the equations of that, or you can look at the book and find out. It immediately sets how much energy is available to power the solar wind with a realistic, quasi-realistic temperature gradient. It still doesn't explain why these temperatures of the electron and proton populations are different. That comes up in another question. So I'm going to go to the next question. No, I'm going to do one more thing here, just as a side note. Sometimes you will see people say, well, the solar wind is like a Laval nozzle. And I thought, okay, I'm going to work this through. So you can read this through at your leisure later on. But the equivalence of the Laval nozzle, of basically pushing a wind through a pipe with a constriction somewhere, and pushing a wind out of gravity, the gravitational well of the sun, into the heliosphere, are mathematically equivalent. And it becomes an equivalence when you have a cross-section of your tube that looks like this. Now, here's a part, this R² part is an easy term to recognize. That's just the expansion in the geometry of a sphere. This part would then be the equivalent of the nozzle. And if you go through this, this is something that has a minimum somewhere. It comes down, it comes like this, and then goes up like that. This has a minimum roughly where the gravitational potential energy becomes half of the gas thermal energy. I didn't think this analogy very helpful at all. Other people seem to think it's helpful. The point I'm trying to make here is that sometimes you can rewrite an equation, as we did with the first example, going towards essentially showing you energies rather than momenta and forces. You can rewrite equations that give you an insight into how things actually work. And sometimes you might stumble on an analogy that works for some people, but this one doesn't really work for me. But mathematically, it is there. Now I'm going to come back to these pressures and temperatures. I basically said, why don't you compute the mean free path lengths for collisions between electrons, because those collisions maintain, or would maintain if there were enough of them, a Maxwellian electron temperature and velocity and energy distribution, so that you can talk about a temperature, a characteristic number that describes the shape of the Maxwellian, and compute those values. So here's groups 3 and 1. I'll pick 3 to start from. And interestingly, you did both the same thing. You said, I can start with the electron-electron collision frequency that's tabulated somewhere in the book, or this very helpful Naval Research Lab plasma compendium. You should all have that somewhere on your disks if you don't already. There's a reference to that in the textbook. And then interestingly, you both thought you needed to estimate the collision cross-section, which you don't really need to do. All you need to do is take the typical velocity and divide it by this electron-electron collision frequency to get to the mean free path. Now, you did that basically here, although I think you've got this term upside down, but that's a detail because you did get it right here. And the number you came up with is for the slow solar wind electrons, something like 0.1 AU. And if I go down a little further, your second answer for the fast solar wind electrons is 0.4 AU. And that is not the right answer, although you worked with the right equation. So what happened here? What happened was that both of you, for some reason, for the characteristic velocity to put in here, that velocity, the bulk wind velocity. But the bulk wind velocity is not the velocity at which electrons bump into each other. That's how they flow together. What they bump into each other with is the noisy velocity on top of the bulk velocity, which is in fact their thermal velocity. And if you had taken their thermal velocity, which is not 400, but about 4,000 kilometers a second, you would have found that these values for the mean free path are somewhere between 1 and 3 astronomical units. Now this, what was the other group that did the same thing here? Here too, yes, you went through the same equation. You wrote down that. Why doesn't it keep picking up that so that I can highlight this? You came up with the same equation. You came up with the same numbers because you both put in that velocity here. Wow, why does it do that? Fascinating, this annotation tool. Here's my solution. I said, look, I'm going to use the thermal velocity. I come up with really big numbers of 1 to 3 AU. What does that mean? That means that the electrons don't really collide with each other en route from the sun to the Earth. That means they can't maintain a thermal velocity distribution. There are no collisions. And because they don't collide, they don't seem to be able to push either, because pushing, pressure, is a matter of colliding and pushing things. So what's up with this? This led to a whole a different school of thought about the solar wind. Already very early on, not too long after Parker started this in 1958 and 1960, by 1970, there were other ideas. This is a screen with many words. Don't read them. I'll give you the essence. You can read them at your leisure later. But this was basically the coming of the kinetic idea, the exospheric idea of the solar wind, where people said, look, we have an electron population that moves really fast. Some of the fastest one in that population probably even go beyond escape velocities. So they're going to try to get away from the sun. But if they were to try and get away from the sun, if they really got away from the sun, that would leave a charged sun, a positively charged sun that would pull back on the electrons. And that electric potential would build up to the point that it would pull back the electrons and pull up the ions. So it effectively reduces the gravity working on the ions by countering it in part by an electric potential, an electric field, and it would counter the escape from the sun by the electrons, by the ions pulling them back in their electric field. There's a really good and very understandable read-up of that exospheric model, how it came about here. Now, in fact, of course, neither of these extremes is true. Near the sun, the collisional path lengths are short because the densities are much higher. Further from the sun, the collisional path lengths are large. So the real sun is somewhere in between. It's a hybrid model between this exospheric model in which the electrons pull the ions out and the hydrodynamic in which the ions and electrons push the wind above them out. It seems like a very different perspective. And yet, if they go through the math, they come up with the same answer. Why is that? Well, you can go and read about Parker. I want to go back to what Parker said early on in 1960. Interestingly, he didn't have this problem of long collisional path lengths because he said the densities at Earth are of the order of 100 per cubic centimeter. And in 1958, he actually says they're like 500 ions per cubic centimeter near the Earth. In reality, that number is somewhere around 5 to 10. So he was off orders of magnitude. And because he was off orders of magnitude, the collisional path lengths were short enough for him to just say, we have collisions, period. I don't have to worry. I can describe this wind as a hydrodynamic phenomenon. Interestingly, by the way, he said that people didn't believe what he wrote. So there's an interesting paper in 2014 where he says, hardly anybody believed what I did. And he had a few years of the field to himself. But he did learn things, of course. Parker, who also passed away earlier this year, had really good insights into things. And in that reminiscence, he says this, and I'm gonna read this to you because it's important that you realize that different perspectives often aren't as different as you might think they are. He says this: it is widely believed that the large-scale bulk motion within a body of a collisionless gas or plasma is not described by the Newtonian equations of hydrodynamics. But whether interparticle collisions happen or not, the bulk flow conserves particles, momentum, and energy. And when you write these three conservation additions down, they provide the equations of hydrodynamics with the familiar gradient of pressure, compressibility, etc. So most textbooks derive these hydrodynamic equations from computing the 0, first, and second velocity moments of the collisionless Boltzmann equation, because the first, second, and third moments of the Maxwellian are the number of particles, the mean velocity, and the mean energy. But the simple idea of just maintaining the full integral, so flux conservation of particles, momentum, and energy, can be used directly. Now, I'm waiting for this book that he wrote in 2007 to come to me. It's in the mail. I had hoped I would have seen it now, but I haven't yet, in which he actually pulls this off. But I can imagine what he does. He basically says, look, even in this concept of the exospheric model, even in this concept of the electrons pulling the ions out, they're not moving differentially. They must move together because of this electric field. Ooh, Nick, you raised your hand?
Yeah, I just wanted to, like, how long does it take before you can wrap your brain around this collisional plasma and it becomes intuitive rather than something where I have to go, oh yeah, it's a collisional plasma and I gotta think about it?
I'm not sure what your question actually is. You're asking me how long. I don't know how long, but what's the question?
I'm thinking as you're going through some of this that, like, had I been there at the time, I would have been like, yeah, this guy Parker is nuts.
No, had you been there at the time, you would have said, this guy Parker is brilliant, except people didn't. there's this story that he often told, that when his paper was submitted, two referees, eminent people, he says, because they were anonymous, but eminent according to the editor, said, this is nonsense. One of them said, go spend some time in the library before you start writing about these things. But Chandrasekhar, who was the editor at the time, told him, look, if you think you're right, I'm going to publish this, because these people may complain, but they haven't told me what they think is actually wrong. And at the time, there was nothing wrong with it, because the density estimates were such that they thought they were talking about hydrodynamics with lots of collisions. It's only later, when spacecraft were flying through the solar wind, and Marcia Neugebauer and others discovered that these densities were really low, that people started realizing, hey, this is an actual problem. And by 1972, you can see the alternate models of people going through the collisionless exospheric model. But as I said, they came up with the same answer, because the bottom line of everything is the available energy to push a certain mass out. And whether you do an integral first and then come up with the energies, or look at the details of the velocity distributions and then do an integral to see what comes out in terms of the solar wind, Parker says here, doesn't matter. Does that make sense? I hope it makes sense. We can come back to this if you want.
Sure.
And Gene Parker was a colleague with Chandra in the same department at University of Chicago. So as an early assistant professor, so be nice to senior professors that happen to be editors.
Yes, he really did appreciate Chandrasekhar's independent spirit, that he basically overwrote these two referees, and said, no, they're not giving me a reason to reject it. I'll go publish it. And fortunately, he did. I hope this makes sense. You can read this at your leisure, and I should have said this. I'm available for questions now or later, or anytime you want to ask questions and have something answered in a Zoom call, as far as I'm concerned, or by email, please feel free, okay? That's what the school is for. I'm gonna go to the next issue. The next question was, start with this momentum equation that we've been looking at before, and show the usefulness of this parameter called plasma beta. Now, I don't know how you all use plasma beta. Sometimes my colleagues will just say beta, and I always get confused about, is this the plasma pressure over the field pressure or the field pressure over the plasma pressure? So I say plasma beta, it's the plasma pressure over the field pressure. That gives me a hint as to what I'm talking about. Anyway, how do I get to that number out of that equation? Groups 4 and 6 worked on this. So, and interestingly, you did both about the same thing. The group 4 did something completely different, and group 6 did something that I thought you would do, but both are elegant solutions. So group 4 said, look, I can start with this, I have to highlight this again, this momentum equation, do some math here that I'm not going to go through, juggle some 4 pi's, and I think you mistook one 4 pi too many that's floating around that shouldn't be there, and came up with a rewrite of that equation here that essentially shows elegantly that there is a term in here that reflects the distortion of, if you want, the actual gas pressure by this ratio beta that sits here. It tells you that there's a part in the plasma that acts as a pressure term. And in this way of rewriting that equation, they showed elegantly that, yes, you can just combine them into the same gradient term. It's the gradient of the pressure, that is the force. One note here is that in an ionized plasma, the pressure is 2 nkt. And I think that means that you're off by a factor of 2 here. And I also realized that I need to fix the textbook in that. And that everybody needs to be very explicit about what you mean by a plasma density. Often the plasma density, say, of the solar wind around the Earth, if you look this up, what they're giving you is the ion density. That's not the particle density. The particle density is roughly twice that because there's about the same number of free-flying electrons around, and both terms contribute equally to the pressure. So you need to be careful whether you use an NKT or a 2 NKT, that you define the N appropriately and take the right value. So I will correct that in the textbook and explicitly say I'm talking about ion densities in the tables that you were working with. Group, where am I? 4, 6, did it the way I thought you would do it. And he basically said, look, this is my equation that I've now ended up with. And I'm going to look at scales and basically saying there's a B and a gradient. So that's a B squared over length scale. And there's a pressure, which is the pressure over a gradient over some typical length scale. And if I take the division of these two, then I get into something that is the plasma beta. And you came up with the right values, except that, as I said, I should have said ion densities, and it would have been a factor of 2 different. Both of these computations essentially say, look, near the Earth, the plasma beta is around unity. So near the Earth, the plasma should be able to distort the magnetic field. Near the sun, the plasma isn't strong enough because the field is much stronger. But there's a however here, and I'm going to come back to that. There's another plasma beta, of course, that can be derived here by taking this term as a pressure. It's pushing, that's the inertia of the plasma pushing compared to the magnetic field resisting such a push. And then you get to a ram pressure plasma beta, which becomes important when we're talking about the solar wind coming into an object that is magnetized like the Earth, which we'll get to a bit later on. However, I said, argue for the fact that you can ignore the magnetic field in Parker's original solar wind model. Well, that was a bit of a trick question because Parker said in his original model, the first half of his first paper says, I'm going to assume a radial flow. I'm going to ignore rotation. If you ignore rotation, also the magnetic field will be perfectly radial. And if the magnetic field is perfectly radial, then there's no curl to it. So the curl of B is 0. And if the curl of B is 0, that's the current density, J, then J cross B is going to be 0, and J cross B is the Lorentz force. So you can make these estimates of the plasma beta, but in this case of a perfectly radial field, the magnetic field cannot exert any forces on the plasma. So yes, you can ignore them because they're truly intrinsically ignorable. The bottom line of it, though, is that you can see people work on equations like the momentum equation and work through it this way by orders of magnitude estimates, by just estimating values and gradients. The only thing you have to be careful with, I would say, that in doing that is two things. One is you need to make sure that the forces that you're talking about actually can do something, otherwise you're misestimating, as I just argued. But also, you have to think about scales. In many cases, there are many scales involved, and processes that are ignorable on one scale are not necessarily ignorable on another scale. This is particularly true when you have cascades of things. So in turbulence or in convection, particularly compressible convection as it happens in the sun, or in places where there are really large gradients, like in shock waves, where you have to be very careful with this kind of estimates. So this was, where are we currently? I'm going to go through this one, and then we probably reached a point where we can take a break, either here or after the next one. This was basically saying, look, there's this elegant equivalence between the solar wind pushing out the sun's magnetic field and a problem in electrostatics that I don't know what textbooks you've used, but you typically come across this mirror charge concept. That if you want to make sure that you describe the field at a point in where you force the field to become radial at some distance from a surface with charges on it, you can introduce a mirror charge on a parallel surface. I'm going to show you that in just a moment. And the question was, if you take this concept of the charged source surface model, show me what the field would look like if you did draw the fields above a surface that had a few bipoles, north-south, 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 next to each other. Interestingly, groups 2 and group 8 both chose to ignore that. You didn't do mixed polarities. The result is that you're coming up with something that isn't quite what I had in mind, but we'll look at what you came up with. And the second question was, and then show me if you do this in a spherical geometry, that if you have this concept of the field becoming radial at some distance d, that you have to put the charges at d squared and that they have to be minus d times the strength of what you have on the surface. If you do that, you, by the way, you have a really easy way of computing field lines of a very good approximation of what the solar wind is actually doing, of telling you really very nicely where the coronal holes are from which the open field connects into the heliosphere. It's something that's still very often used. It's much, much easier computationally than MHD. It's not as good. It doesn't do dynamics. It doesn't let you propagate explosions through a field like that because it's a potential field. But in terms of understanding the 3D geometry, it does a really good job. And I'll show you how it does that in just a moment. So, but first I'm going to go to group 2 here. So group 2 said, that's what you meant. I have this charged surface here with 3 pairs of bipoles. No, they're not 3 pairs of bipoles. This is just one dipole. This is one charge up here and another charge down here. And this is what the potential field above it looked like. What's wrong with that picture? I'm going to sit here for a moment and hold still. So in here, there are field lines going from one polarity to the next. I guess they go from the red to the blue because that's the way you colored it. And up here, there's this current sheet in my potential field. What's wrong with that? I'd like to have one person speak up. At least. Yes? Oh, come on. It's not a really difficult question. Anyone? I can't hear you, Nick. I see your lips move, but I can't hear you.
When you say it's not a difficult question, that means everybody's going to dive under the table.
No, okay. Let me be specific about this. It's not a difficult question. I didn't say the answer was difficult, and now I'm being difficult. Okay. No, I just gave you the answer in the sentence. What's wrong with a current sheet in a potential field? You can't have a current in a potential field. There is nothing there to carry a current in a potential field. In fact, in this case, where I should have said a vacuum field, and then maybe it would have been clearer, there would have been no particle to carry a current. But you can't have a potential field model and a current. They are mutually exclusive. I guess you have to realize that, because interestingly, the other group did much the same thing. You basically also ignored, well, you said, I've got 3 pluses and 3 minuses, but I wanted them mixed together. Which you didn't do. And you also said, well, I can get an X point. Yes, X points, neutral points, points where the field disappears, do exist in potential fields. But this current sheet does not exist in a potential field. What I would have liked to see is something like this, where I've taken a surface down here with 3 dipoles here of equal strength, and I've put anti-dipoles up here in the mirror surface. And if you do that, then in this intermediate surface here, all the field lines are going to be perfectly radial to that dashed line. In here, I actually managed to draw a field line that hit exactly that null point. Here and here, I missed the null point. There are null points there, just the field lines didn't hit them because I only had these 3 pairs, so there's no translational symmetry in here. You'd have to have an infinite series continue on both sides here to put them at exactly the same positions. But you can get these null points. Now this would suggest, can you please pay attention to what I'm going to say, because this is the answer to one of the questions coming up shortly. This would suggest that every dipole has a null point above it. On the sun, that is not the case. Well, it has null points floating, but not on the source surface. And the reason for that, you can see if you look at this one. Now, it's the same geometrical principle. All I've done is changed the strength of these 4 to be, I picked a number, 3 times stronger than the others. Now that introduces a really big dipole, essentially, from these 2 big ones that overarches the others. So now the null points that existed here over these charges have essentially vanished. You see this big swath of open field. This is essentially the equivalent of the open field reaching into the heliosphere on both sides of one polarity here, this box polarity, call it negative, and of the other polarity here, coming out of this one, the diamond, so call it positive, with a null point in the middle. And that null point is essentially the equivalent of a helmet streamer that you'll see in solar eclipse pictures. How does that work? Well, I took a series of surface magnetograms and computed the source surface equivalent, now in spherical geometry, and said, where do I find this cap that closes off all the field underneath it? And from where do the open fields reach into the heliosphere? Much of the time, the solar field will be like it is in this diagram, sort of a tilted dipole field, where on one side, field going into the heliosphere lands on one polarity, and on the other side, it lands on the other polarity. So there's a, say, north polarity here and a south polarity here, and in between sits this helmet streamer belt, which has null points. In fact, it's a whole null line going around the sun. At other times, when the polar fields on the sun are not quite as strong, the dipole moments of all this mixed polarity here becomes more dominant. And that means that on the largest scale, again, this is beginning to answer a question that comes on later on, there's more undulation in that heliospheric current sheet. There are, if you now imagine you're the Earth at this latitude of roughly plus or minus 7 degrees, but roughly 0 degrees in terms of the sun rotating by, you'll see one polarity come by for a while, then the other polarity, then the other polarity. So here there are 4 polarity reversals as the sun rotates underneath the Earth. Here there are only 2. Sometimes that one helmet streamer belt can actually become multiple helmet streamer belts. like in this case. So here there's one polarity coming out of here, and actually the same here, and the opposite polarity comes out in a belt around the sun. This thing undulates and changes depending on the evolution of the surface magnetic field, which I hope you will learn about later on in the school, as the active regions on the sun come and go. This is the underlying structure that essentially gives rise to what you see during an eclipse. And this is one of these beautiful eclipse pictures that Shadia Habal and Druckmüller have made, where they combined the two visible coronal lines, visible in the visible domain and therefore visible from the ground, so the things called the green line, the coronal green line and the coronal red line, combined in one picture. Yes, sir. Nick, you have a question?
Well, I was just going to ask on the previous imagery with the helmet streamers. So it's difficult to tell from the magnetograms that you have underneath them. But are those primarily from solar minimum, solar maximum throughout the solar cycle?
Okay. It actually tells you here in the caption, if you go through it. This is a simulated cycle where we basically mimicked the solar properties as best we could in terms of active regions evolving, emerging, disappearing, with the modeling of the flux transport and the polar fields, etc. And we said, we'll take this 11-year sunspot cycle and we'll look at it somewhat out of minimum on both sides here, the beginning and the end, and in the middle near the maximum. So these are phases of essentially a quarter. I think it's, you can do the math. You divide this by 11, you'll get the phases in the solar cycle. Okay.
So the rising phase into solar maximum.
Yes.
Got it. Thank you.
And yeah, and you can go backwards in the same sequence to understand what happens as you go the other way. There's this large-scale polar dipole that varies in antiphase with the sum of all the dipoles of all the active regions around the activity belt. They alternate so that you get this swing from a nearly dipolar to a quadrupolar field and back to a dipolar field, but now flipped around. I hope that someone like Mark Chung or the other lecturers on the solar wind will get into that in more detail. If not, ask me. I can get back on this if you want.
So I'm sorry, D is the lower left-hand corner, and that is at solar maximum?
Well, I can understand your confusion because it shouldn't be.
Okay.
Huh? Yes, I will look into that, and I'll have to see what I mistyped here.
Excellent. All right, thank you. I'm sorry to I thought I was confused. So, but now I see. So my intuition is usually you get these nice streamer belts confined to the lower latitudes at solar minimum or near solar
around time of solar minimum. Yes.
Right.
Yeah.
And you get the wonky. So that's the ballerina skirt as compared to the can skirt.
All right.
Right.
Yes. Although ballerina skirts droop, and they rarely do in the case of the sun, sometimes by a few degrees, but not that much. They're mostly sort of symmetrical about the equator, but we're getting into details.
Okay, great. All right.
The principles of what I was saying are correct, although the phasing may be slightly off. So
yes, absolutely.
I will look into this, and I may have typed in the wrong numbers and selected the wrong examples to put this together. I hope not. But you're right, it's a little odd. I'm going to ask you all another question. This one I will not say is easy because it isn't, but it is an important one to understand, particularly in the theme of this summer school, the coupling of systems. So, where are these helmet streamers located? There are papers even, and even on Wikipedia, if you look at it, you'll find that these helmet streamers supposedly develop over active regions on the sun. Is that right or is that wrong? See, now it's a complicated question with a simple answer.
Can we do that? Can we do a thumbs up for it's right and the surprised open mouth face for wrong?
Sure.
Okay.
Let's try that.
So where are the helmet streamers located?
Are they associated with active regions?
Yes. So I saw one thumbs up from one brave soul, but that's about it.
Wow. So there's a lot of doubt here.
Oh, nope, we're getting more. Getting some answers. Sometimes you have to repeat your answer because it goes away pretty quickly. But it looks like it's a split.
Ah. Well, that means that the answers are random. Or it might mean the answers are random, or maybe they have been reading different papers or thinking about this slightly differently. All right. Yes, even on Wikipedia, as I said, it says helmet streamers are bright loop-like structures. Oh, they have loops in them, yes, which develop over active regions on the sun. Now, if you were very lenient, you'd say, yeah, they might have, they're over active regions because active regions are everywhere. But no, they are not specifically associated with active regions. And the answer to that, I'm going to go back to here, is already in this diagram. Like, there's an active region here that has a helmet over it, but there's a bipole here that does not have a helmet over it. And it's even clearer if you look at this. There are gazillions of active regions and their decay products on these surfaces of the sun. And there are not very many helmet structures. So either this potential field source surface model fails miserably, and it doesn't, or the association with specific active regions isn't there. And it isn't there. There's a study, I'll give you the reference in just a moment, and you can see that in the file, that explains this very elegantly. It basically says, no, it's a line of sight integration thing. You're looking through this scattered light in the green and red lines, electron scattering light from the solar surface out, in an eclipse picture, you would see scattered electron light, and that would show you these things. In the green and red line, you're actually seeing collisional excited ions de-excite into these photons emitting stuff towards you. And you're looking through an optically thin plasma over the entire depth of the solar corona. Where they integrate strongest is where you have the longest path length. So look at this image up here. Let me get rid of some of these annotations. Okay, come on. This is the point where you have the longest path length. And here's another longest path length. That's where you would see most of the structure in these helmet streamers. In a picture like the bottom one here, you'd have to think about this for a while. Where am I integrating? Well, probably somewhere here, certainly here, maybe here, and probably here. And that, if you go to this paper by Yimin Wang, Neil Sheely, who are legends in this field, they essentially said it very elegantly. There where the latitudinal variation as a function of longitude reaches an extremum, so where you go through this point that you have the longest potential sight line, and there where that is really into the plane of the sky, that's where you see these helmet streamer structures. So the sun connects into the heliosphere everywhere. You are tempted to think that its field is closed underneath it over active regions. Well, it is low down, but the large scale structure of the sun is really determined by the larger scale structures in the field. So the polar fields, except at times of solar maximum when the polar fields are weak, and the summation of all these active region fields that have come up and are dispersing over the solar surface into sometimes accidentally organized large patterns. And it is these large patterns that set the coupling into the heliosphere. And that, I think, is a great point to take a break, isn't it? It's been about an hour.
I think, yes. So let's take a 10-minute break. So be back at 1:15.
And if you're motivated during this break, type in a question or two. I'll come back to what I've discussed so far and then continue with the rest of the activities. Okay?
Great.
Great. Okay. Maggie's on top of things and recording again. Okay. Since Nick asked this question about the phasing of these heliospheric coupling, I dug up the movie that I made out of this simulation. And it is a movie that runs for 11 years and takes 4.5 minutes. I'm not going to do the whole thing, but I'm going to give you the beginning of it. So let's see if I can actually share the screen again. Yes, go ahead. Are you seeing a segment, at least, of a movie here? Is that moving?
Yes.
All right. So this is the simulation running where active regions are beginning to pop up at cycle minimum going into the cycle. You'll see that mostly north-south dipole dominating into a flat current, flat basis of the current sheet, so this helmet streamer belt, but pretty quickly it actually begins to undulate out of it. So that phase of near symmetry of just flat into the solar equator, into the ecliptic, is not very long. This is a movie where you're looking at the sun from a co-rotating perspective, so you're not getting confused by the sun rotating. The changes that you're seeing in this simulated helmet streamer belt, it's apparently rotating and evolving because of the differential rotation of the sun. And you can see the differential rotation in the active regions, that the higher latitudes are drifting backwards and the mid latitudes are drifting forward relative to the reference latitude, which is the Carrington latitude at 27 degrees. And you can see that most of the time it's nicely dipolar. It may be tilted, but it's dipolar. Even at cycle maximum, sometimes it's dipolar. And here you can see this trumpet opening up and merging into the dipole again. So this is it's a pretty dynamic structure, all potential fields. And now all you have to do is imagine through this coronal mass ejections, etc., running to make it even more exciting than this. Does that give you enough of a view, Nick? I think I got the phases right. I will now compare that with the caption to the figure, but I think they were right, these snapshots out of this movie.
Okay.
Anyway,
yes.
I'm going to go back to part 2 of the question that we left with, which had to do with show me that the strength of these mirror charges has to be minus d times the surface charges if the source surface is at d and this mirror surface is at d squared. By the way, I know this is a horribly confusing terminology. Technically, the source surface, the surface with the mirror sources, is at d squared if the heliospheric source surface is at d times the solar radius. I don't know how this came about. I think it's because the heliospheric physicists think of the source of the solar wind as coming out from the point that the solar field becomes nearly radial. That's at about 2.5 solar radii. But the mathematical equivalent, say in Jackson's textbook on electrodynamics, is the surface, is that you put the mirror surface, the mirror charges at a surface at 2.5 square. So there are two different surface charges, just to confuse the world. Anyway, I thought I have to compliment Group 8 because they came up with a really elegant solution that avoids a lot of math by saying the following. Well, obviously, at a surface where the field becomes radial, we're actually talking about an equipotential surface. Yeah, I had actually managed to forget that. But you can think of it in terms of magnetic monopoles or electric charges is easier. If you have a surface where the field is normal to that surface, then moving a charge along that surface has no component of the electric or magnetic field, so the charge can't gain energy, therefore it must be a potential, an equipotential surface. So that leads to a really simple equation that they're trying to solve. And then they said, geometry is also really simple because there are these similar triangles. You can realize that, oh, I'll try. The ratio of that branch to this branch is the same as the ratio of, and I have to get it right, this branch to that branch. And because they share this common angle here, they're similar triangles. And therefore, the answer is very easily there. You get to a charge that has to be minus d times the charge of the surface. It's almost embarrassingly simple. I did it much more complicated. I said, look, I'm going to start with a field from a monopole that's described by that equation there. And I'm going to say that the sum of these two charges, the field has to be perpendicular to the tangent to the circle. So I did a dot product and I come up with this equation, and out comes the same answer. Interestingly, if you actually did the math of the equation that Group 8 came up with, this one, and work out r and r primed, you get to exactly the same equation, not surprisingly, because you have to get to the same answer. But I thought this is a really elegant way of doing it. So if you like, look at their solution and say, yeah, that's neat. It hardly takes any math to get to that answer. So I'm going to move on to the next one. This is an easy one. How long do the slow and fast solar wind streams take to get to the Earth? This is basically just to get you an idea of what's happening. How big is the solar system? Something that moves at 400 or 1,000 kilometers a second still takes days to get to the Earth. The answers, of course, are found by just dividing a velocity over a distance over a velocity. And the answer is somewhere between 2 and 4 days for the fast and slow solar wind. In that time, by the way, the sun has rotated over an angle of somewhere between, what was it? 25 to 53 degrees. And the importance behind that realization sits in knowing where solar energetic particles come from, predominantly. You have a geometry that looks something like this. This is a simple sketch of this potential field source surface model inside this sphere, where the source surface model, the heliospheric source surface model, sits here at about 2.5 solar radii. And beyond that, you get this thing that's either referred to as the Parker spiral or the Archimedean spiral, which is the same thing. And you can imagine that if there's a flare going off somewhere in here, in this active region, and it finds some way to connect to field going out along this spiral to, say, the Earth sitting here, well, at 200 solar radii, so quite a bit off the scale of this diagram, then it will look like these particles, that the particles arriving will actually be coming from a position that's typically somewhere like 40, 50 degrees off central meridian towards the west. This is confusing, particularly to people in Australia, because east and west are reversed. But when solar physicists say east and west, they actually mean a geocentric east and west, not a heliocentric east and west. So west is on the right and east is on the left, as opposed to pictures of Earth from space where this is the other way around. This is annoying, but no, from space it's the same. From you sitting on Earth, it's the other way around. But it's east and west means east and west in the sky that you're looking at. So it comes predominantly from something like out here. And you can also see why there is this spread, because after all, underneath that source surface or the inner solar corona, the connectivity of field lines is basically determined by how things map back down onto the solar surface. And energetic particles come from a range of these different positions. So it's not like necessarily the heliosphere connects to the wrong thing, although it does vary depending on whether you're looking at a slow stream or a fast stream. But on top of that, there's also this dispersal of the near solar field that can cause the source region of energetic particles to not quite be at the same latitude all the time. Okay. There was a question F about factors that limit the fidelity of the sun-planet couplings via the solar wind. And then there's a question G, I'm going to let you choose, which had to do about these physical processes common to the solar, stellar, and exoplanetary space physics. Do you have a preference, Nick? I can start with either, or I can skip one, or I can skip both, but I guess that's not what you'd like to do.
I think they're both really good and accessible questions and things we want to consider throughout the entire school. So
okay.
I certainly want to see them both. I would start with F. I'd take them in order, but F is
I think that's a great idea. I was going to say, let me start with G, because if I start with G, then we can discuss why these models don't work so well a little after. So let me start with G. Now, you all gave excellent answers in many different formats and many different degrees of wordiness. I took the liberty of condensing them. I'll be happy to go back to any one of those that you gave, but what I did was basically compile a list of these processes that you all came up with. And I've got the numbers here of what group said it. And pardon me, I did take the liberty of paraphrasing what you said to get to common terminologies. And sometimes I may have read something in your words that you didn't quite put there, or you might have put things in your words that I didn't read into them. So apologies for that. But it's basically a pretty long list of processes. And that's exactly the idea of heliophysics. There's a lot of processes that are common, but whose parameters differ. So they may manifest differently, or appear to manifest differently, or appear to have different relative importances in different settings, but they all somehow get in here. Now, most of you voted for these top two groups. One, obviously, everywhere we have flows and everywhere we have waves. We have flows and waves that can be described in terms of hydrodynamics in the neutral atmospheres, in terms of magnetohydrodynamics in the heliosphere, the sun, the magnetospheres in general, and the heliosphere. There are also waves in seismology, of course, which are interesting because they are in fact directly known as diagnostic tools. Helioseismology and geoseismology, planetary seismology, also recently available on the moon and on Mars, give us insights into domains that we can't see any other way. So we know about the solar interior because of seismology. We know about Earth's interior because of geoseismology. Another phenomenon that was mentioned because of flows and waves, of course, are shocks that happen all over the place. Shocks that happen, as we know, in the heliosphere and near the sun, where they generate energetic particles. Shocks that happen whenever the solar wind bangs into an object, a magnetic object or a magnetized object, at least some conductive object, because I'll get to that question in just a moment. What happens when the wind hits something like the moon, which is non-conducting, is interesting. So let's get back to that. Shocks also happen in neutral atmospheres or in the solar atmosphere because of the stratification of density. That because the density drops with height, the amplitude of a wave will grow. And if the dissipation of that wave is fairly slow, then the amplitude can grow to a point that you're suddenly looking at a shock wave. You can have a shock wave running up into the Earth's atmosphere. And in many people's minds, shock waves running into the solar chromosphere from the convective motions underneath contribute maybe significantly, maybe not, and probably certainly position dependent to the heating of the solar chromosphere in points where the magnetic heating is not dominant. Turbulence. Turbulence has gotten not enough attention in the heliophysics textbooks. I don't know how that happened. There is a chapter on heliospheric turbulence, but in the summary book, this principles of heliophysics that you've been looking at, turbulence isn't really mentioned at all because it somehow didn't connect enough in what was written about in the other books. That's unfortunate because that's also a process that happens all over the place. It's important for scale coupling. It's important on the sun in how magnetic fields are turbulently shredded to a scale where they can dissipate effectively. In the heliosphere, turbulence turns out to be an important process to add some additional energy to what is otherwise dominated by the electron energy conduction. Turbulence inside atmospheres or convection as one phenomenon into which turbulence can come helps to mix chemical gradients inside stars, inside planetary atmospheres. So yes, it's a very important process. Winds from stars are interesting. Winds that which is a flow, which hit planets, but also at times hit other stars, or in binary components, two stellar winds that collide with each other somewhere between these two stars. There's an interesting concept here. If you have a binary system, and by the way, 1 out of every 2 stars that you see in the sky is actually a binary or more complex system of stars, that when you have 2 stars orbiting each other at a distance that is greater than their relative radii where the winds become super alphanic, they don't know about each other magnetically. Somehow these winds collide somewhere in the middle, but the magnetic signals can't be communicated from one to the other. So their coupling is entirely gravitational and through mutual irradiation, which sometimes becomes important depending on what star is being irradiated and which one is doing the radiating. But if you put these stars closer than their relative distances to their super alphanix point to each other, they can communicate with each other magnetically. So in the tightest of binary stars, you can have magnetic fields actually connect from one star onto the other. And that might actually lead to some of the really large flares that we see in stellar binary systems. But modeling that has been really complicated because we have so little observational knowledge of what the magnetic field patterns on these rapidly rotating stars actually look like. That's a different topic altogether. So yes, flows and waves are all over the place. So is this sort of what you'd like to do, Nick? Just talk through where we see all these processes and why they're important? Or would you like me to take a different tack on this? Otherwise, I'm just going to continue.
I think this is fine. You know, what do other people think? Are there questions on where these processes are important? Or you know, I think this is also a good tour of some of the things that we are going to run
Right.
into throughout the summer school. And
So I'll
it's
continue
also-
and I'll continue until we hear somebody with another question,
So
and then I'll
somebody's-
be happy to go into that.
Okay, great.
Second, equal number of votes, I would say, the processes of dynamo. By the way, I have to come back to this. Now, it's not like we don't know what dynamo is, but actually dynamo to different communities might mean different things. To an ionospheric physicist, as I understand it, dynamo action means there where the field performs work on the plasma. It's basically something, the field is moving the plasma around, that's called dynamo action. To an astrophysicist, dynamo in a star really in most cases means the entire cycle of making the magnetic field and maintaining the magnetic field, and as in the case of the sun and many other stars, actually cycling the magnetic field through different patterns. There are other terms like that where different communities talk differently. The thing that has always puzzled me, and I know why it came about, but I still find it confusing, is that there is this domain in the Earth's atmosphere that's called the ionosphere thermosphere, which is basically saying, here, there's a mixture of ions and neutrals in this domain. And when I talk about the ionosphere, I'm talking only about the ions. And if I talk about the thermosphere, I'm only talking about the neutrals, but they're coupled. Stellar people, solar people, in particular in the heliophysics arena, have the same problem when they talk about the photosphere and the chromosphere. Particularly the photosphere is really mostly neutral with a small component of ions. The chromosphere has far more ions, but also mixed with neutrals. But we don't call them different things. We call them this one domain of these coupled gases is the chromosphere. So here and there, you'll find terminologies that you'll have to sort out a little bit. Like, why is the thinking different? And does it matter that the thinking is different? Anyway, going back to the dynamo. The dynamo is important, and its manifestation, if you go through it, really, it relies on a power source. You have to get power in, and you have to get power out. Both are important into the system because you essentially have to set up a temperature gradient that drives convective motions. So inside the dynamo, you can have in a planet residual cooling from its formation, or even in the coolest of stars that are not capable of sustaining hydrogen fusion, you can have long-term cooling going on that releases energy, well, that enables a temperature gradient to be set up to the outside. You can have fusion, like in a star. You can have fission, like in a planet, like in the deep interior of the Earth. You could have chemical differentiation, where there's gravitational settling, sometimes together with solidification deep into the interior. The core of the Earth is solidifying into iron, separating its chemical components, and that releases energy. Or you can even have tides, gravitational tides, like in some of the moons around the major planets that are performing, adding work to the planetary interior and warming to the moon's satellite's interior, warming it up. And then you need to have a power loss. Now, in the sun, that's the atmosphere. It radiates this energy out and thereby becomes cool, cooler than the deep interior is. So there's a temperature gradient in which, in part of the domain, you can set up convective motions. Power loss can happen through the planetary crust. Tectonic motions are an important part of removing energy from the Earth's interior. The absence of tectonic motions in, say, Venus is probably one of the multiple reasons why Venus does not have an active dynamo. It does not have these convective motions in its interior because the temperature gradient isn't sufficient, on top of probably the fact that it's rotating very slowly. Now, I mentioned oceans here, that oceans aren't so much the power loss, but actually oceans, water, happen to lubricate the planetary crust. So on Venus, they lost the oceans because of solar winds stripping the dissociated hydrogen and oxygen of the water and the vapor in the atmosphere a long time ago. And as a result, its planetary crust is less lubricated, and that's reduced the power that it can lose through its surface, which made the dynamo disappear. Anyway, all these processes are important, and the combination of the two, power source and power loss, plus the one important ingredient a dynamo must have, the preferred direction, which is usually induced by rotation, enables dynamos to function. Obviously, the word reconnection appeared in many of your returns. Reconnection is one of these processes that happens all
Karel,
over
can I
the
interrupt
place.
before you go on to reconnection?
Yes.
So there is a question in chat. So from Hasna.
Is power loss related with force? There are forces that have to function in order for convective motions to be set up. So in that sense, yes, there's a force. What I mean is literally the loss of thermal energy, so random energy that is extracted on a star by radiation, and in the Earth by the mantle taking energy by convecting, by moving and by conducting energy out of the interior. So it's a loss of thermal energy. It's a sink.
Does that help?
Mark just made a comment. I see that I'm going to try and get back to also in a moment. Great. So,
and before as you go on, so Mark had a useful suggestion. If the participants can put into chat what a general area that you're working in, like one or two words, and then which of these processes are important in that area. So I'm thinking, for example, like solar, and dynamo and heating might be an answer to that question. So just in chat, you can add what you're, just to get an idea of which processes people are most interested in. And then Raphael had a question about remnant magnetism.
Yeah, that's poorly positioned in this sentence. Remnant magnetism, as I understand it, is the magnetism left over in the planetary crust after the dynamo starts functioning. So Mars is a good example. Mars doesn't have an active dynamo, but there are locations on the Martian surface and in the Martian atmosphere and outer atmosphere where there still is a magnetic field, just because it happened to be frozen in from past dynamo activity. So it shouldn't be there as a power loss. It's basically, I've tried to flag myself, I should have mentioned this, so I'll try to rephrase that before I send this out. Reconnection, yes, is an important one. I've always struggled with, can you define reconnection for me? Because reconnection is a funny thing. You have to remember where it comes from. When magnetohydrodynamics was developed, it was quickly realized that the equations and the behavior of the magnetic field became a lot more tractable if you ignored resistivity, if you ignored magnetic diffusion. That gave rise to what we now know as ideal MHD. And in ideal MHD, you can show that the plasma, once stuck on a field line, is stuck on that field line forever. The plasma moves the field moves the plasma, they have to move together. And reconnection was introduced as a consequence of saying, well, but there has to be some form of dissipation, diffusion of the magnetic field, because otherwise I can't change the magnetic field topologically. And if you want to change it topologically, you have to break the field lines. Now, field lines don't actually exist. They're mathematical constructs. They help us think. And in frozen in ideal MHD, field lines are the paths of the particles, well, spiraling about them, but the centroids of their movements are along the field lines. So they introduced this concept of reconnection, where you can clip the magnetic field and connect different atmospheres. So there's one definition that says it's basically where you connect, where you allow parts of field lines to jump from one plasma volume to connecting to another plasma volume, or slide if you have diffusive process. To me, reconnection merely means that where you have reconnection, it basically means your basic assumption failed. There is no such thing as ideal MHD at that point, and field line concept fails. So, but you all recognized reconnection was one of these things that we see everywhere in space physics, in astrophysics, and in planetary, magnetospheric, heliospheric physics all over the place. So yes, MHD also introduces all these things that are basically the structures into which magnetic volumes are partitioned, mostly temporarily, but they help us think in terms of things of current sheets, remember, not in potential fields, flux ropes that I haven't mentioned, but you'll get to, ropes that basically carry some current, or a curl of B that creates a rope, flux tubes that I should have mentioned here. There is, of course, the discussion in MHD about collisional, collisionless that I already described earlier on, that although you might think collisionless, that still doesn't mean that they're uncoupled. There's the complication of a neutral component. Neutral components in a plasma that happen in the Earth's atmosphere, in the solar atmosphere, in neutral particles coming in from the interstellar medium and penetrating through the collisionless, mostly collisionless heliosphere, and then through charge exchanges suddenly become part of the plasma, etc. And if you want to really complicate things, dust, because by the time you start thinking about formation of stars in dusty settings, or comets flying through the heliosphere, we have an extra complication. There's a chapter on dust in one of the heliophysics books. It isn't mentioned in the summary. Can't fit everything in, but it's something you have to mind. Then there is tides and torques. Tides come in different forms. For an atmospheric scientist, there is the tide of the irradiating sun onto the rotating Earth. For some compact binaries, for planets around other stars, that is an important tide to have. Then, of course, there is the gravitational tide, and that is basically working to synchronize orbital and rotational motions, like the moon around the Earth. If you look at some exoplanets close to their stars, they basically, through gravitational tides, have become synchronized so that they always turn the same side to their star, which sets up a really interesting atmosphere, really hot on one side and really freezing on the other, and this ring at the terminator where maybe the temperatures are acceptable. They're called eyeball planets, if you want the technical terms. Then there is a set of processes that have to do with radiative transfer. Radiative transfer was conveniently ignored in just about everybody's presentations because it's so complicated, maybe, but it's really important. It essentially determines how things couple through photons, how things lose energy or can gain energy by radiation in or out. It's complicated once we start talking about clouds. Clouds on Earth are one of the most complicated factors in climate modeling because we still don't really understand the dynamics of clouds. But clouds and the associated things that have been called greenhouse gases, carbon dioxide, methane, ozone, complicate radiative transfer, radiative exchange from one object to another because they are essentially able to stop the free radiation of energy from, say, a planetary surface out to space, thereby changing the temperature. This is one of the things that happened on Venus. The greenhouse gases became so dominant that the temperature of Venus shot up into hundreds and hundreds of centigrade, and it became most unpleasant setting in general, apart from the chemical setting. In stars, cooler stars in particular, where neutral atoms and sometimes even complicated chemicals like carbon monoxide and water can form. Anything with 2 or more atoms in a molecule to an astronomer is generally complicated, particularly to stellar astrophysicists, except in cool settings like in sunspots or in the coolest stars. But also in other stars, this thing that they don't refer to it as a cloud, they refer to it as line blanketing. So if you create enough spectral lines that can absorb energy coming out of the photosphere, you can modify the energy loss from the star, modify the surface temperature, in fact, thereby modifying the entire interior and then certainly the dynamics of the near surface layers. Radio transfer is important for some winds. Hot stars they're so bright that their light pushes the wind out rather than that coronal heating, which they don't generally have, pushes their wind out. So radiation pressure in hot winds is important, and radiation pressure is important also for comets, their tails at least, and for dust in the near sun environment. Well, then there's convection. Yes, there's a lot of convection going on in neutral gases, atmospheres, in magnetized plasmas, in the sun, in the ionosphere, convective motions, advective motions, I would say. Convection in magma, coupling with rotation. Something that I missed when I started making this list was, of course, chemical processes. Yes, chemical processes are important. Chemical processes, if you want to think about it a little more broadly, I would almost take these two sets together, something like a phase change. A chemical process is literally a combination of neutral atoms, but you can also think about it in the ways that ions and electrons, or ions of different ionization states, or ions and neutrals combine or not combine and change things. So, but phase change is an important one. In obviously atmospheric processes called rain, literally water rain, but there's also this thing called coronal rain. And that technically, and that's why I'm saying be careful with your terminology, is not rain. It's not a condensation into a fluid. It's a densification that looks like a dark absorbing object floating and falling down through the corona because its mass is no longer supported by the pressure of the gas underneath it, and it's falling down, but it's not really rain. Neither is, at the case of a solar flare going off, heat being conducted into the chromosphere, this gas going up, literally evaporation, because it's not a transition of a phase, although it is going from a high, very dense medium into a far less dense medium with pressure density gradients of factors of 10,000 or more, easily achievable in the sun. So you might call it evaporation, but it's not really the phase change that we mean with proper evaporation of water into gas, liquid water into gaseous water. Interestingly, magnetic instabilities were only mentioned by one group, and then in fact only for flares and CMEs. But of course, magnetic instabilities happen all over the place. Magnetic instabilities is what makes space weather in the magnetosphere interesting, because those are instabilities in the geotail that propagate into signals in the ionosphere, and that can migrate into couplings of space weather into electrical systems, power systems, and large-scale conductors on Earth. So they can be driven by the evolution slow of the field. The slow differential rotation of the sun sets up huge filament systems that can become coronal mass ejections, or they can be formed by the emergence and intrusion of new field into a setting, like new dipoles coming up onto the solar surface. or external driving, like the solar wind's variability hitting a magnetosphere and somehow triggering instabilities in the reconnection in the front end or in the tail end, leading to an instability in the system. The last few, these three, I'm not sure I would call them processes. The existence of an exosphere, yeah, obviously energy conversion is an important one. I wondered why only one group mentioned that. Because you can, in heliosphere, we're converting energy all the time. We're converting magnetic energy into kinetic energy, either bulk or thermal, or the other way around. We're using radiation as an intermediary between a star and a planet. So there's a lot of energy conversion going on. The conversion from from radiative transfer in the stellar interior to bulk kinetic convective motions in the convective envelope. So it's an important one that we see everywhere. You should all ponder this and put this more higher up in your list. Why did nobody mention particle acceleration? That one puzzled me. You may have all thought implicitly, well, if I've got shocks and reconnection, I'm accelerating particles. But I would have liked to see it mentioned separately anyway. What shapes all these things?
Can we make a list in chat of all of the energy conversions that the specific energy conversions that people think about when they?
Yeah.
Yeah. So
I'm having a hard time. I'm having a hard time talking and reading chats at the same time, so I can't.
Yeah,
I can't actually do that.
Yeah, right. So so maybe people can think of a specific energy conversion process that you think is important in your field or in the heliosphere in general, and put it in chat.
As to process it, the parameters involved in shaping these processes, I'm going to go through this really quickly because they're fairly obvious.
Sure.
Yes, geometry, rotation, species and stratifications, the conditions of the plasma, like the ionization degrees and the temperatures and the mean free paths we mentioned, orbital properties, because they set tides, the radiative tides and the gravitational tides, the energy transport mechanisms, do you convect, conduct, or radiate, or do we do it by magnetic fields? The evolutionary phase of a system, particularly a star, but also a planet in terms of, say, comparing the dynamo in Mars and Venus and Earth. Tides, I mentioned, the velocities, the size, the seed field, I'm not sure because it's not all that important. It's hard to imagine anything not having a magnetic field when we start. And most systems actually forget their seed fields because of the dynamo actions going on. One that only one of you mentioned, sort of, the dimensionless numbers. I've talked only one, namely the plasma beta, but it's very interesting if you think about the relative importance of terms in any relevant equation. You can basically derive these dimensionless numbers by comparing them, by doing these order of magnitude estimates that led to our plasma beta estimates. That's an interesting one. If you go to the original chapter in the book by Margie Kivelson, she went through dimensional numbers in terms of how the solar wind interacts with bodies in the solar system. And I tried to mimic some of that in the principles of heliophysics, but it's an interesting way of exploring and determining what process is important where. There's also a specific chapter that I hope you read through that has to do with dimensionless numbers and magnetic reconnection, gyration radii, plasma scales, collision distances, etc. So all of those are important. I'm getting to the end of it. Let me see what else I might want to say. Centrifugal forces, yes, you all did get that right, except for a typo in an exponent. You can find that. The dynamo, why does the Earth's magnetic dynamo look like a dipole? One of you said spherical harmonics. Yes, spherical harmonics. This is going back to how the magnetic field also of the sun couples into the heliosphere. It's the large scales that matter because we're looking at a distance. One of you answered, it has to do for the sun with the strength of the field. No, the strength of the field isn't important. The structure, the geometry of the field is important. The scales are important. The scale of the field of the sun, the largest scales make it into the heliosphere. The smallest scales don't matter. That's the important message of this thing. Yeah, that was that. For planets, you all got estimates of the magnetopause right. And then I thought, when we think about, I'm sorry, I'm running out of time at the geospace. That wasn't my intention. I was hoping to have a little more time at the geospace setting. Magnetospheres in general. One of the things that I puzzled on was there isn't very much matter in the solar wind. Most of what happens that makes space weather, that makes the magnetosphere dynamic, happens because that little amount of matter actually carries with it a magnetic field. And it's the magnetic field that makes the dynamics. With a few exceptions, on a body that isn't conducting, like the moon, you do not induce, there's no intrinsic magnetic field, it has no dynamo, it has no residual magnetic field of significance. Because it doesn't conduct, the plasma in the wind moving by the object does not induce a magnetic field that would resist the magnetic field of the solar wind coming in. So essentially the solar wind basically rams right into the solar surface, into the moon's surface. And I wondered how much matter is there coming down? Because that wind has to sort of leave the moon again, flow around it and be dragged away at a distance. Is it an appreciable amount? And I hope I did the math right. But if you go through it and say, well, I've got an ion density of 10 per cubic centimeter coming in, that's something like 500 kilometers a second. I will accumulate 45 milligrams per square centimeter in 1 million years. There's really no mass in the solar wind. It's all in the magnetic field. I thought it was a stunningly small number. If you multiply that with basically the surface through which that wind is flowing from the star as a whole, of course, you do get to an appreciable number, but it's still very small. It's 1 part in 10,000 over 1 billion years. The solar wind was much stronger earlier on. 1 billion years ago, it probably was comparable to what it is now. A few billion years ago, it was substantially more. But over its entire evolution, the sun has lost only a small fraction of its mass. That's different in the most massive stars. The most massive stars basically blow out their atmospheres under radiation pressure, and they can lose percents of their mass in their very short lifetimes. A low mass star essentially does not lose mass significantly. It doesn't really change its internal structure much, other than by fusion, not by mass loss. I think we're getting to the end of it, except for this comment by Mark. What did Mark say? I have to scroll back to what Mark said. Mark said, oh, you know, in the ionosphere, boy, there's lots of comments.
It was about currents, using
It was about electrical
systems.
currents. Yes,
Yep.
because when you talk to ionospheric physicists, Mark happens to be one, they often will talk about electrical currents. And if you see diagrams of how the solar wind shapes the Earth's magnetic field, you'll often see vectors representing currents. Now, being an astrophysicist, I have great difficulty thinking in terms of currents. In a diagram that describes the magnetosphere of any planet, the only real current that I have to introduce somehow in my thinking is this thing called the ring current, because the ring current is not an MHD phenomenon. The ring current occurs because the gyration of the particles is so large that they actually sense that the magnetic field changes in that gyration. And that causes them to drift. It causes the ions to drift in one direction and the electrons to drift in the other direction. And the more energetic the particle, the larger the spiral, the more they are subjected to this drift. But differently charged particles moving in different directions are a current. So this is actually a real electrical current that I have to keep in my mind that is there. The other currents, I'm not going to say this. I'm going to let Jean Parker say this. Okay, I'm quoting Parker again. You can read this. Parker basically says, look, you can think of J as the cause of B, current as the cause of the field. And that's true in case of things on Earth, because where we set up electrical wires to create something out of which comes a magnetic field. But if you want to treat that with equations, then the only way to do that when you have currents is to do complicated integrals over the entire volume that has all these currents running through it. It is much easier, he says, and more elegant to do this using only B, because with B, I can write down the equations of MHD using a local variable, B, and a local gradient, the gradient or the curl in B. And I can forget about currents because it's all hiding in the geometry of the magnetic field locally. No integrals needed for the system. But he does allow for one exception in this, because he says, in the absence of resistivity, the electric field in the co-moving system, so there's no significant driving of J. But of course, in the ionosphere, it is all about resistivity. And there you can't get away without thinking about currents. And I have to admit, get a headache thinking about currents and the way that the Hall and other resistivities deflect the directions of motions because of these currents and thinking about it. It's really tough for an astrophysicist to think about currents. So you'll have to pardon us as a community for having difficulty with that. I think with that, I'm gonna just stop because although K is interesting, okay, I collected what you all said, and there are some words in here. We can get to those if you would like to discuss that. But I'm going to stop talking here and let Nick decide on where to go or not to go with this. My hours are pretty much up.
Great. Thank you so much, Karel. So questions. I don't know. So Christina asked if we skipped F. I think you.
Yes, we did.
Okay.
But I'll be happy to. I'll be happy to have a quick look at it. I did the same thing. I basically collected all your input. F would be sort of here, I guess. Yes. Going through this quickly, it basically
is about the issues. Like, what are the issues with some of the models, right?
Yes.
Yeah.
Right. What limits their truthfulness, their applicability, their fidelity?
Right.
I've seen many of the answers in the responses. There are, I think, two things that dominate in all of this. One is, well, this one. We basically have a system that is huge. The Earth is 200 solar radii away from the sun. The magnetosphere is vastly bigger than the Earth. The heliosphere is a really big system. The dissipative processes, the shocks, the instabilities, the reconnection processes all happen on very small scales, hardly bigger than, say, gyration radii, sometimes even not even gyration radii. So MHD models have to make assumptions about a separation of scales, the big scales that we describe by averages, the small scales that we describe by hand waving, by basically saying, there's turbulence going on here. I'll describe this by a fudge factor that I'll call diffusion or effective resistivity or something like that. We can't model the entire range, but the entire range is in fact coupled. So your choices of where you couple, the choices of where you go from a hydrodynamic to a particle kinetic scale, for example, in some of the hybrid codes currently being used, are important in the consequences of how the system works. Not necessarily the bulk of the system, as Parker argued, because the hydrodynamic equations follow from the integral behavior of everything, but the details matter, and that the details are what are space weather. The details are what most of you are studying. So that's a tough one, scales. The other that keeps coming back also has to do with scales, but now come into observations. We have dozens of spacecraft flowing around the Earth, orbiting around the Earth, doing in situ measurements, remote sensing measurements. Not very many at all in the heliosphere, and certainly not anywhere far away from the Earth, closer to the sun, except for one occasionally flying through now, and the solar orbiter doing its very best to be around there too. But imagine one measuring point for in situ processes in something the size of the heliosphere is a bad set of initial conditions to guide your MHD models from. On top of that, we can't really measure what we would like to measure. You'd like to measure the state of the magnetic field. Well, near the Earth, you can't see the state of the magnetic field. You have to sample the state of the magnetic field by a few spacecraft flying through there. So you'll sample it here and there, but you'll not get a complete description to start your MHD models from. You have to make assumptions. And it's really hard to get these assumptions to actually mimic what happens in the real world. In the case of the sun, we can only use photons, and we can only use photons where they're actually coming from and are useful to us. Polarization of photons is really hard to utilize in the X-ray and EUV domain because our optics really aren't capable of doing it. We do it in the visible domain, sometimes in the near-infrared domain. But by the time we're looking at the visible near-infrared, we're looking only at the solar surface. So we can only see the surface domain through which the magnetic field is peaking. But we can't measure the vector magnetic field very well. We can measure the line of sight fairly well over a fair part of the front side of the Earth-facing side of the sun, but not the vector field. The vector field is out of which you can compute the curl of B. You can call this a current, or I can call this the non-potential part of the field, the energetic, energy-carrying part of the field, the part of the field that actually leads to instabilities like flares and coronal mass ejections, and even the work that's done in coronal heating through non-potentialities in the magnetic field. We can't very well measure them. We can't certainly measure them well enough. And once the CME goes off, for example, that's a field configuration in the corona where we don't know and cannot successfully so far model. So whenever a CME goes off, we don't know what's actually leaving the sun, magnetically speaking. We might measure, we used to be able to measure it with the stereo spacecraft, and at least one side is coming back again. So we can measure how fast coronal mass ejection is moving towards the Earth. But we can't tell the modelers what is going to hit the Earth in magnetic terms. Not until it passes the point where we have upstream wind measurements, which is only 1 million miles from the Earth, about an hour, half an hour away. And that's not enough to actually measure the field and run through a full simulation of what the magnetosphere is going to do. So the electric power people would love to know what a coronal mass injection is going to do. All we can effectively tell them is give them a guess of when it's going to arrive, but we can't tell them what it's going to do. This is equivalent to me telling you on your birthday, where you're setting up for a barbecue party in the garden, that 2 hours from now, the weather is going to change. And I cannot tell you whether it's going to get better or whether you're going to be hit by a cyclone. And that's not a good state to be in. So those are basically the problems. You can go through this list in a little bit more detail, but it basically says the same thing over and over again. Lack of observations and an enormous range of scales. Was that fair enough, Christina?
Yeah, I think it's great. Obviously, there's lots of details in here, but you hit my favorite one, which is lack of measurements. So,
All right. All righty.
Yeah, and the other thing for any complex coupled system, we often try to think of what numbers could describe that system. And for ionosphere, you know, tell me the density or the temperature and its flow or something like that. But recognizing that it's has structure and energies flowing in multiple directions. How do you describe the magnetosphere? You know, is it Kp sufficient? Is the standoff distance? So everything we can measure is a proxy or is not really important for what we really want to know in terms of energy content or things like that. So it's like a doctor, you know, I can give you my BMI and weight and resting pulse rate and cholesterol levels and all these things, but does it tell me about my health? So.
And the problem with most of these models, there's two kinds of models, right? There are those models that we use as a laboratory, models that we would like to learn lessons from how things actually work and what processes are most important where. And there are models that we use to forecast. This is where you get into space weather. Forecasting is even more difficult than nowcasting or reproducing states that look like what we're actually experiencing, but not in great detail. And even on the largest scale, here's one, a forecast of the solar dynamo. There were these exercises of comparing dynamo models, seeing which models work best. They picked the one at the Space Weather Prediction Center that seemed to be the most promising. So there's a forecast for what's called the current cycle, solar cycle number 25. And then there's the actual solar sunspot number. It's only a factor of 2 off. But a factor of 2 is basically what we've seen in cycle variation through the last few centuries. So it's essentially off about as much as it can be. And that's our best guess. It's a sad state to be in. In fact, it's worse than you think, because we think that we understand why the sun has a solar cycle. But more than half of the stars like the sun do not exhibit a cycle. That's a little off heliophysics proper, but the knowledge of what other stars do will help us understand what this sun does, as the knowledge of what other planetary magnetospheres and ionospheres are doing nearby that we can actually fly to, help us understand what the Earth's magnetosphere is doing. Different settings.
Also like to point out, Karel, in this particular plot, I think there's a couple different things, right? It's not just how big the maximum is going to be or how big it is at any given time, but there's also the timing of the peak, right?
Yeah.
And that has huge implications. As, you know, there are spacecraft that are planning or targeting a particular time in the solar cycle, whether they're going up because they want more events or they want it to be quiet. And then, of course, when we talk about the manned space program, there's a whole issue about, like, when do you send people on long journeys to, you know, eventually say Mars or something? And do you do that when things are really quiet, or do you do them when they're active? And if we can't even predict when the peak of the activity is going to happen,
Right.
it makes it hard to make these long-term plans because everything's planned years and years in advance because it takes a while to build all these things.
And then there's this one that doesn't even do one peak, just
Right.
for the fun of it.
Right, just because.
And then of course I'm gonna stop sharing this screen so you might see me a little bigger. There are these short-term forecasts, like when does an energetic particle event happen? There's this story about the Apollo mission flying to the moon in 1972, but if they had been off by a few, was it weeks or 1 week, they would have flown through an energetic particle storm that might well have made them, if not seriously ill, suffer from bad consequences of radiation poisoning. We can't forecast things on a timescale of hours to days to years. So we're not quite done. In that sense, everybody here is going to make useful contributions to this, I hope, learn from all of this. And I hope that eventually we're going to get to a state that we can do better to protect assets and people in space and on the ground. Oh, and I didn't even mention that solar variability. Who knows what it has to do with climate? Or maybe we should all argue that it doesn't have anything to do with climate and get people to go in the right direction and do something. Okay, this is getting into politics.
Well, at that point, I'm going to cut you off.
All right.
I'm not going to cut you off. I will. I ask you to stick around if you can for a little while. I've got about 10 minutes of logistics for the participants to do. But then, if there are any questions or comments or things you want to talk to Karel about, if he can stick around for 15, 20 minutes after that, that would be great.
Yep, I will.
And have our sort of first true office hours that we are trying to in order to mimic the discussion or questions after the when people run up to the podium after the lecture as the lecturer is unplugging their computer and start asking them questions. Well, we've kind of built that into this and this time, given that we don't have that sort of impromptu effort. So that would be great.
Yep.
Okay. So all right. So given that, I'd like to transition into giving you some instruction for your time zone group work for today, which is going to set us up for our first lab exercise, quote unquote lab exercise for tomorrow. And so in the Slack channel, I've put, so Maggie, are we set up to go into the time zone group breakout rooms? Is that?
Right after this?
Yeah.
Yeah, yep, we're all
Great.
good.
Okay, just wanted to make sure you were there.
Yep.
In the Slack channel, I put 2 documents. You are going to, this is a throw you into the deep end and then come fish you out if you start to drown exercise. So we're going to give you some data and some model results from an event. And I'm switching things. Last night I got a bug on, Mark and Christina, and I switched the event to the Starlink event in February. Okay, which is it's a fairly straightforward event, I think, and we can. But I thought it was relevant and a little bit exciting. So for those of you who don't know, SpaceX has this program, Starlink, to launch dozens or hundreds, I'm not sure what the number of satellites, but a lot of little satellites into low Earth orbit to provide internet connectivity, which is both inspiring and terrifying all at the same time. But they had a problem in February. There was a geomagnetic event at just the wrong time. And when they were trying to do something clever in very low Earth orbit, and they lost a batch of satellites that they had just launched. So I thought it would be a good idea to look at that event and analyze it. And so you're going to do this in total of 3 rounds. First, you're going to work in your time zone groups, and each group has been assigned a particular domain of solar, wind, magnetosphere, and ionosphere. And this may not be your particular expertise, but I'd like you to at least take a shot at doing that. And they're to start with that tonight, tomorrow, in the next 20 something hours, right? You're to start that. When we come back together tomorrow, you're going to set yourselves up in your synchronous groups and decide which of you is going to become an expert in the particular domain area that you want to look at. And so you're going to look at one of those 4 domains, become an expert in that, and then come back together and explain it to everybody else in your synchronous groups to share what you learned about your particular domain and how it all fits together as part of a larger system, right? So this is a systems approach to this. Part of it is for you to just get a review of what the total system looks like and a reminder of what some things are involved in that, so that as we go forward, you'll see, you'll be prompted for some things that you've already seen. This is a sort of the point of this school, and part of what Karel's message is that these processes are run throughout the entire system. So this exercise sort of breaks it down into the standard domains, but then I want you to put it back together again by the end of tomorrow into a broader system. All right. I hope that wasn't too confusing, and maybe as you see the exercises, you'll see what's happening there. So the 2 documents are, one, the lab manual with general questions for all of the expert areas, but also then specific questions that you should look at. And then which in the, and I'm going to share my screen here. And then in this document, which has a lot of stuff going on, I'm not sure why, but in this document, I've assigned for the time zone groups, the 8 time zone groups, each group has a specific area of questions and data that they should be looking at for this event. All right. And what I'm going to recommend now is we have, I'm going to stop sharing my screen. We have a few people, a couple of people who are new and just coming in, maybe not for the first time, but are had some struggles during the pre-sessions. What I'd like to recommend is that the 8 time zone groups get together in their numbered rooms. So now if you're time zone group 1, you'll go to room 1, time zone group 2, go to room 2, etc. Maggie, do you have the time zone group assignments handy?
I can make it handy. Give me just a second.
Okay, can you drop that in chat? In the meantime, I'll I'll answer Brandon's question.
Hi, yeah. So I just wanted to confirm that the time zone group and the sync groups that we just got out of are different things, right?
Yes. So the time zone groups, because we're split up, and I'm sure the people in India and China are dying to go to sleep right now, and so they can meet tomorrow morning. So we're split up across time zones. So, and then the synchronous groups are your our attempt to like say, okay, let's meet with other people who you haven't talked to yet. So,
okay,
great,
cool.
Can you
Thank you.
repost the synchronous groups?
So right now we will repost the synchronous groups when we need them. So
Okay.
right now we're working on the time zone groups, and that is what Maggie just put in the great. Thank you. Okay. Any other questions as to what we're doing? Great. Why don't we open up the rooms, go into your breakout rooms for your time zone groups, and decide on what time you're going to meet and to review the portion of the event that you've been assigned. I've been trying to decipher how much lag there is in what we're saying, and then what some of the people who may be less connected are seeing. Oh, so which group is Raphael in? Raphael, do you know where you're going?
I believe group 6.
Okay. I think you can assign him.
Hello, Maggie. I think there was some error. I got this invitation to join group 3, but I am 6.
Perfect.
You should be able to. Okay. Yep, Maggie,
yes,
take
so
care of it.
Yep, are you able to join group 6? If not, I can put you in there.
I can, but I just notify it because there might be someone else who is supposed to be in group 3.
Okay, great. Thank you.
Yeah. All right. Thank you.
Junali, you're in group 7.
Okay, great. All right. Carl, thank you for doing that. I think it was good setup. I'm a little surprised that we didn't get as much interaction as I would have hoped, but we'll have to continue to work on building the group. So so it'll be something to just for us to watch for. But certainly you made great use of their input.
Would you like me to do anything else?
Other than when we come back from this, which I think should only take about 5 minutes, let me, if you can hang around for a few minutes and see if there are any questions, that would be great. Okay. Whoop. I'm gonna go check and see. Maggie, can you just push Trinali into group 7 and I'll see if she's there
I
along
did.
with
Yes, I did push her in group 7. So I don't
came
know if
back. Okay.
she has to accept
She has
it.
to accept it. Okay. Yeah. All right. Great. I'm gonna check in with them and see how they're doing, and then we'll probably close this. Oh, there's only one person in group 4. I'm gonna check on that.
Okay.
Okay. Give me a thumbs up if you were able to organize yourself and find a time to meet, or figure out how you were going to meet, or give me a surprise face if you were not able to do that and need a little more time, either a little more time or a little bit of support with that. I'm seeing mostly thumbs up. So, are there any questions as to? Oh, okay. So,
can they make their own time zone Slack channel?
they can absolutely make their own time zone Slack channel. Yes, I think they can. I think they're allowed to make that, and certainly they can DM each other. And if you need it, if you need me to make a Slack channel, let me know. Okay. Ashtush, did Group 6 have trouble finding a time to meet, or?
Yeah, we sort of were agreeing on the topics to choose and the time. We'll need a little more time. I guess after this is over, in our Slack channel, we can communicate and fix something.
That would be great.
Yeah.
Okay. That sounds like a plan. Any questions as to what the assignment is? Oh, Suvik. Suvik.
Yeah, Nick, I have a specific question to you. So I really didn't understand what our instruction was. So you are saying that we will meet in our time zone group. For us, it's going to be tomorrow. So, and then we will discuss the activities that you have given. And then when we are going to meet the sync group, like tomorrow itself.
When we're together again. Okay. So tomorrow. Okay. So for you tomorrow night when we're together again. So the sync are for synchronous. That is when we're together, right? So we're all in synchronous time. Okay.
Understood.
Okay. Good.
Thanks.
Any other questions, Brandon?
All right. So I just want to make sure I understand this clearly. The group work that we have to do with our time zone groups, we have to all do that together, compile it, and discuss it amongst ourselves, make sure we all are experts in that particular field. And then tomorrow when we meet in synchronous meetings, each of us are going to be in different synchronous groups, and we have to explain what we would have discussed together in our time zone meetings to those in groups. Is that what the exercise is?
We're going to have another sort of expert group. So almost, we're going to have another expert group meeting tomorrow, because I've not guaranteed that everybody in the time I'll explain how that's working tomorrow. For now, take a look at just that one set of data. I just want you to get warmed up, and then I'll explain more tomorrow about how we're going to organize things.
All right.
Okay. So we'll do it one step at a time.
So we're just looking at the data, answering the questions in that lab thing, compiling it, and then tomorrow when we do it, what are we doing in our sync groups tomorrow?
I will explain that tomorrow.
Okay.
Let's take it one step at a time. Raphael.
Nick, I just need some clarification. You know, when we met in our time zone meeting group, we observed that we have observational data questions and modeling data questions. Are we to do both, or we have to choose any of the one?
Say it again. You had which
I
questions?
we observed that we had two sets of questions. One was based on observational data, and the other one was based on simulation.
You should look at both.
Okay, that's just what I wanted to clarify.
Great.
Thank you.
Good. All right. Any other questions? Going once, going twice. Okay. Karel will still be here for people who have questions about any of the activities or have comments on his text. He definitely wants any input for improving the text. And if you have that, stick around, and he will be answering those. And if not, we are gonna we'll call it a day. And thank you for participating in our first session, and look forward to a couple of weeks of excellent work. All right, good. All right, we'll see everybody tomorrow, but stick around if you have questions for Karel.